There is a place in space where time stops, where the laws of physics as we know them cease to function, where reality itself folds inward and disappears. And right now, at the center of our galaxy, 26,000 light-years from the chair you are sitting in, one of these places is waiting. Its name is Sagittarius A star. It weighs 4 million times more than our Sun. And it is, by every measure we have, the most powerful permanent fixture in our cosmic neighborhood. We call it a black hole, but that name doesn't begin to capture what it actually is. It isn't a hole, it isn't empty. It is a region of space-time so violently warped that nothing, not matter, not energy, not even light itself, can climb back out once it falls in. For decades, black holes lived only in the mathematics of general relativity, strange solutions to Einstein's equations that most physicists assumed nature would never actually build. Then we found them, thousands of them. And in 2019, using a network of telescopes spanning the entire planet, we did something that should have been impossible. We photographed one. But here is what no image can show you. What happens at the boundary? What occurs when you cross the line where escape velocity exceeds the speed of light and the universe stops obeying the rules? What it feels like when space itself begins to stretch you apart? And what waits at the center, in that mathematical point of infinite density where every equation we trust breaks down and returns nothing but nonsense? This is the story of black holes. Not as abstract concepts, but as real objects with real consequences. Objects that don't just destroy, they keep secrets. Secrets we may never be able to retrieve. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The universe has a way of building monuments to its own violence. We look up at the night sky and see points of light, clean, orderly, permanent. It is the most comfortable lie the cosmos has ever told. Because most of those points, the bright ones, the ones that anchor constellations and guide ships and inspire poetry, are not peaceful. They are factories, furnaces operating at scales that make our sun look like a campfire. And when those furnaces finally run out of fuel, some of them do not fade. They do not cool into quiet cinders, they collapse, and in collapsing, they create the most powerful objects in the known universe. Black holes are not born from nothing. They are not random tears in the fabric of space, cosmic accidents waiting to swallow the unwary. They are the end products of stellar evolution, the final chapter in a story that begins in clouds of gas so vast you could fit 1,000 solar systems inside them and still have room left over. Those clouds are called stellar nebulae, enormous regions of hydrogen and helium, leftovers from the Big Bang, mixed with trace amounts of heavier elements forged inside earlier generations of stars. They drift through the galaxy, cold and dark, for millions of years. Then something disturbs them, a nearby supernova shockwave, the gravitational pull of a passing star, a collision between two clouds. The disturbance doesn't need to be dramatic, just enough to start the process. Gravity takes over, the cloud begins to contract. As it does, it heats up. Pockets of gas collapse faster than others, fragmenting the nebula into dozens or hundreds of separate clumps. Each clump continues to collapse independently, pulling more mass inward, spinning faster, flattening into a disk. At the center of one of those disks, pressure and temperature climb. Hydrogen atoms slam into each other harder and harder. Eventually, the core gets hot enough, around 10 million degrees, that hydrogen nuclei overcome their mutual repulsion and fuse into helium. The moment fusion ignites, a star is born. Not just any star. For the story we are telling, we need a massive one, at least 8 times the mass of our Sun. Preferably more, 20, 30, 50 solar masses. Stars at that scale live fast. Our Sun has been burning hydrogen for about 4.5 billion years and will continue doing so for another 5 billion. It is middle-aged, stable, unremarkable. A massive star burns through its hydrogen in a few million years. Some of the truly enormous ones, the blue hypergiants weighing 100 times what our Sun does, exhaust their core hydrogen in less than 1 million years. Cosmic mayflies. They shine brilliantly, far outshining anything in their neighborhood, and they die young. During the main sequence phase, while hydrogen is still abundant in the core, the star is in balance. Gravity pulls inward, fusion pressure pushes outward. The two forces hold each other in check. The star is stable. It sits on what astronomers call the main sequence, a diagonal band on a graph, where most stars spend the majority of their existence. Then the hydrogen in the core runs out. For a star like our Sun, that is the beginning of a long, gradual decline. The core contracts, heats up, and starts fusing helium into carbon. The outer layers expand into a red giant. Eventually, the star sheds those layers as a planetary nebula and leaves behind a cooling white dwarf. End of story. Massive stars do not have that luxury. When the hydrogen in the core is gone, the core contracts and heats up just like in smaller stars. But because the mass is so much greater, the gravitational pressure is enormous. The core gets hot enough to fuse helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. Each stage happens faster than the one before. Helium burning might last a few 100,000 years. Carbon burning takes a few centuries. Oxygen burning is done in a year. Silicon burning, the final stage, lasts about a week. By the time you have an iron core sitting in the center of a massive star, the outer layers are still fusing lighter elements in shells above it. The star has become an onion, layers of different elements stacked on top of each other, each shell burning at a different rate, the whole structure held together by gravity and radiation pressure in a precarious, temporary equilibrium. The star has expanded enormously by this point. It is now a red supergiant, hundreds of times wider than it was on the main sequence. If you replaced our Sun with one of these objects, its surface would extend past the orbit of Mars, maybe past Jupiter, depending on the star. From the outside it looks calm, a dim reddish glow. Inside it is a ticking bomb. Iron is the end of the line. Fusing elements lighter than iron releases energy. That energy produces the outward pressure that keeps the star from collapsing. But fusing iron costs energy. It absorbs energy instead of releasing it. Once the core is mostly iron, there is no more fuel, no more fusion, no more outward pressure. Gravity has been waiting. The moment the iron core can no longer support itself, it collapses, not slowly, not gradually. The collapse happens in about a second. One moment, you have a core the size of Earth weighing more than the Sun. The next moment, that core has been crushed into a sphere 10 miles across. 10 miles. The density at that point is beyond anything we experience in daily life. A sugar cube of neutron star material would weigh more than 1 billion tons. More than every car on Earth combined, compressed into the volume of a dice. The collapse does not stop gently. The core overshoots. It compresses past the point where the neutrons can support it, then rebounds. That rebound sends a shockwave tearing outward through the star's outer layers at a significant fraction of the speed of light. The shockwave hits the infalling material, still collapsing inward, and reverses it. The outer layers, all those shells of oxygen and silicon and carbon and helium, are blasted into space. We call that explosion a supernova. For a few weeks, a single dying star can outshine an entire galaxy. Billions of stars, all their light combined, and the supernova is brighter. The explosion is so violent that it synthesizes elements heavier than iron, elements that cannot be made any other way. Gold, platinum, uranium. Every atom of gold in every ring, on every finger on this planet, was forged in a supernova. The blast wave carries all that material outward into the interstellar medium, enriching the clouds that will one day form the next generation of stars. Without supernovae, the universe would still be hydrogen and helium. No oxygen, no carbon, no iron, no planets, no chemistry, no life. Supernovae are the reason we exist, but this is not the end of the story. It is the middle, because something is left behind, the core, the thing that collapsed in the first place. It is still there, sitting at the center of the expanding debris cloud. And what happens next depends entirely on how much mass is left in that core. If the core weighs less than about 2 to 3 solar masses, the collapse stops. The neutrons, packed so tightly that they are practically touching, generate what physicists call degeneracy pressure. It is a quantum effect, a consequence of the Pauli exclusion principle, which says that no two fermions can occupy the same quantum state. Neutrons are fermions. When you try to compress them past a certain point, they push back. Not because they are hot, not because they are fusing, just because quantum mechanics says they have to. That pressure is enough to halt the collapse. The core stabilizes. You now have a neutron star. A sphere of neutrons 10 miles across, spinning rapidly, often emitting beams of radiation from its magnetic poles. If those beams sweep past Earth, we see them as pulses. We call those objects pulsars. Neutron stars are fascinating in their own right. They are the densest, stable objects in the universe, but they are not black holes. If the core weighs more than about 2 to 3 solar masses, degeneracy pressure is not enough. Gravity wins. The collapse continues. There is no known force in physics that can stop it. The core keeps shrinking, 10 miles across, 1 mile, a few meters. The density climbs past anything that has a name. The equations of general relativity, which describe how mass warps spacetime, start giving answers that do not make intuitive sense. The curvature of spacetime becomes so extreme that a boundary forms. A surface in space beyond which nothing, not matter, not light, not information of any kind, can escape. That boundary is called the event horizon. At this moment, a black hole is born. The transition from core collapse to black hole happens fast. Some sources say it takes a few seconds. The star that took millions of years to evolve, that spent centuries burning carbon and neon, that took a week to fuse silicon into iron, collapses into a black hole in less time than it takes you to tie your shoes. Not every supernova makes a black hole. This is important. The explosion and the remnant are related but not identical. A supernova is what happens to the outer layers. The black hole, or neutron star, is what happens to the core. You can have a supernova that leaves behind a neutron star. You can have a supernova that leaves behind a black hole. In rare cases, you can have a core that collapses directly into a black hole with almost no visible supernova at all. The star just disappears. Astronomers call those failed supernovae. The core collapses, the outer layers start to fall inward, but the shock wave never makes it back out. The whole star just falls into the black hole it created. Observed from outside, the star dims and vanishes over the course of a few months. No explosion, no flash of light, just gone. The mass threshold is not a hard line. Whether a given core becomes a neutron star or a black hole depends on more than just its mass. It depends on how much mass the star lost during its life, how fast it was rotating, whether it had a binary companion stealing material, how the supernova shock propagated, and how much material fell back onto the core after the initial explosion. Some of the physics involved is still being worked out. Simulations of core collapse supernovae are among the most computationally intensive calculations in astrophysics. You are trying to model nuclear physics, general relativity, magnetohydrodynamics, and neutrino transport all at the same time in 3 dimensions. The computers run for months. The results are approximate, but the basic picture is clear. Massive stars die violently. Some leave neutron stars. Some leave black holes. The dividing line sits somewhere around 3 solar masses for the remaining core. For the star as a whole, you typically need at least 8 solar masses to trigger a supernova in the first place. Stars more massive than about 20 solar masses are almost guaranteed to leave black holes behind. In between, it depends. There are even mass gaps, ranges where direct collapse is less common. One gap sits roughly between 2 and 5 solar masses. Another sits between about 50 and 150 solar masses. In those ranges, the physics of the collapse gets strange. Pair instability supernovae, where the core produces so many gamma rays that they spontaneously turn into matter-antimatter pairs, can blow the entire star apart with no remnant at all. The universe, it turns out, has opinions about which masses are allowed to form black holes easily and which are not. Stellar black holes, the ones formed from collapsing stars, typically weigh between 5 and a few dozen solar masses. They are the smallest category of black hole. Intermediate mass black holes, if they exist, weigh hundreds to thousands of solar masses. Supermassive black holes, the ones sitting at the centers of galaxies, weigh millions or billions of solar masses. We do not fully understand how those larger ones form. They may grow from stellar black holes that merge and accrete material over billions of years. They may form from direct collapse of enormous gas clouds in the early universe. They may have been seeded by the first generation of stars, which could have been much more massive than anything we see today. That is a different story. For now, we are focused on the ones we understand best, the ones formed from stars. The ones we can trace from birth in a nebula to death in a supernova, to rebirth as something that warps space-time itself. You cannot see a black hole directly. By definition, no light escapes from inside the event horizon, but you can see what happens around it. Matter falling toward a black hole heats up. Friction in the accretion disk, the swirling ring of gas and dust spiraling inward, heats the material to millions of degrees, hot enough to emit X-rays. Those X-rays we can detect. Binary systems where a normal star orbits a black hole are some of the brightest X-ray sources in the galaxy. The black hole pulls material off its companion, and that material screams as it falls. We have found dozens of stellar mass black holes this way, watching their companions wobble, measuring the orbital period, calculating the mass of the invisible object. When the mass comes back above 3 solar masses and no light is detected, the conclusion is unavoidable: black hole. The process that creates them is not rare. It is a standard phase of stellar evolution for any star massive enough to trigger it. Our galaxy contains an estimated 100 million stellar mass black holes. Most of them are invisible, drifting silently through interstellar space. leftovers from stars that died millions or billions of years ago. Every few decades, somewhere in the Milky Way, another massive star runs out of fuel and collapses. Another black hole is born. We do not usually see it happen. Supernovae in our own galaxy are rare from our perspective, maybe a few per century, and most are hidden behind dust clouds. But they are happening. Right now, within a few thousand light years of where you are sitting, there is probably a red supergiant star with an iron core that is hours or days away from collapse. It will happen while you are asleep, or at work, or reading this. The core will implode. The outer layers will explode, and in the space of a few seconds, a new black hole will be added to the galaxy's collection. That star has already lived its entire life. It formed, burned hydrogen for a few million years, swelled into a supergiant, and built an iron core. All of that is done. The clock has run out. Gravity is about to collect. And when it does, the result will be an object so dense, so extreme, that it will warp the space around it into a shape nothing can climb out of. A trap built from the collapse of a star. A region where the rules change, where time slows, where light bends. Where, if you get close enough, the universe itself stops making sense in the way you are used to. We call the edge of that region the event horizon. It is the boundary between the universe we know and the universe we cannot see. It is the point of no return, and understanding what it actually is, what it means to cross it, and why nothing that falls in can ever come back, is where the story gets strange. We left off at the edge. The moment a stellar core collapses past the point where anything in physics can stop it. The moment space-time itself warps so severely that a boundary forms, a line in space that once crossed cannot be uncrossed. That boundary has a name, the event horizon. And despite what every science fiction movie has ever shown you, it is not a glowing ring of fire, it is not a shimmering membrane. It is not a wall you can touch or a surface you can stand on. It is something stranger. It is the point in space where the rules governing cause and effect stop applying the way they do everywhere else in the universe. The term itself was coined by Wolfgang Rindler, a physicist working in the 1950s, who was trying to find a clean way to describe the boundary of a region from which no signal could ever reach an outside observer. He called it an event horizon because events occurring beyond it are forever hidden from view. You can never see them. You can never know what happened. The horizon separates the observable universe from a region that is, in every practical sense, gone. To understand what the event horizon actually is, you need to understand escape velocity. This is not a concept unique to black holes. It applies to every massive object in the universe. Escape velocity is the minimum speed you need to travel to break free of a gravitational field without any additional propulsion. Throw a ball upward from the surface of the Earth, and it slows down, stops, and falls back. Throw it faster, and it goes higher before falling. Throw it fast enough, about 11 kilometers per second, and it never falls back. It escapes. That speed, 11 kilometers per second, is Earth's escape velocity. It is not the speed you need to reach orbit. Orbit is different. Orbit is falling sideways fast enough that you keep missing the ground. Escape velocity is the speed you need to leave entirely. Every object with mass has an escape velocity, and that velocity depends on two things: how much mass the object has and how close you are to its center. The more massive the object, the higher the escape velocity. The closer you are to the center, the higher the escape velocity. For Earth, 11 kilometers per second at the surface. For the Moon, much less. For Jupiter, much more. For the Sun, about 618 kilometers per second at its surface. Still nowhere near the speed of light. Light travels at roughly 300,000 kilometers per second. For most objects in the universe, escape velocity stays comfortably below that. You could, in theory, build a rocket fast enough to escape. But as you pack more and more mass into a smaller and smaller space, the escape velocity climbs. Shrink the sun down to a sphere a few kilometers across, and suddenly the escape velocity at that surface jumps dramatically. Keep shrinking it, and at some radius, the escape velocity hits the speed of light. That radius is called the Schwarzschild radius. It is named after Karl Schwarzschild, a German physicist who derived the solution in 1915 while serving on the Russian front during World War I. He solved Einstein's field equations for the specific case of a spherical, non-rotating mass. The result was a formula that told you exactly how small you would need to compress a given mass before its escape velocity reached the speed of light. For an object with the mass of our Sun, that radius is about 3 kilometers. Compress the Sun down to a ball 6 kilometers across, and the escape velocity at its surface would equal the speed of light. Go any smaller, and the escape velocity exceeds the speed of light. At that point, nothing can escape. Not a rocket, not a bullet, not a beam of light, because nothing in the universe can travel faster than light. This is not an engineering problem. It is not a question of building a better engine. The speed of light is a fundamental limit baked into the structure of space-time itself. According to special relativity, as you accelerate an object with mass closer and closer to the speed of light, the energy required to keep accelerating it increases without bound. To actually reach the speed of light would require infinite energy. You cannot do it. Light itself travels at that speed only because photons have no mass. Anything with mass is stuck below it. So once you are inside the Schwarzschild radius, once you have crossed the boundary where the escape velocity exceeds the speed of light, you are trapped. Not because there is a wall, not because something is holding you, but because every direction you could travel, every path you could take, leads further inward. Space-time itself has been warped so severely that up no longer exists. Outward is no longer an option. You can fire your rockets at full thrust. You can point yourself away from the center and accelerate as hard as physics allows, and you will still fall inward. The event horizon is that boundary. The Schwarzschild radius marks where it sits for a non-rotating black hole. It is a sphere. Every point on that sphere is the same distance from the singularity at the center, and every point on that sphere represents the last moment at which light emitted outward could, in principle, hover in place. Cross it by even a millimeter, and that light falls inward. This is worth pausing on, because the behavior is deeply counterintuitive. From far away, outside the black hole, space-time looks normal. Clocks tick at their usual rate. Light travels in straight lines. Gravity behaves the way Newton described it, more or less. A spacecraft orbiting a black hole from a safe distance would experience gravity the same way it experiences gravity orbiting a star of the same mass. Nothing weird happens as long as you stay far enough away, but as you get closer, space-time begins to curve, noticeably. Light no longer travels in straight lines. It bends. Clocks no longer tick at the same rate. Time itself runs slower the closer you get to the event horizon. This is not an illusion. It is not a trick of perception. It is a real, measurable effect, predicted by general relativity and confirmed by experiment. If you could somehow survive near the event horizon of a black hole and then return, you would find that far less time had passed for you than for everyone who stayed far away. Time dilation becomes extreme near the horizon. A clock sitting just outside the event horizon, as measured by a distant observer, would appear to tick slower and slower. As it approaches the horizon, each tick takes longer. At the horizon itself, from the perspective of someone far away, time stops. The clock never quite reaches the horizon. It asymptotically approaches it, the ticks stretching out toward infinity. An object falling toward a black hole, as seen by a distant observer, would appear to slow down, redden, and fade as it neared the event horizon. The light coming from it would be stretched to longer and longer wavelengths, redshifted by the extreme gravitational field until it faded into invisibility. The object would never appear to cross. It would just hang there, frozen at the edge, dimming into nothing. But that is the view from outside. From the perspective of the falling object, something very different happens. To someone falling into a black hole, there is no moment where time stops. There is no barrier. There is no sign that says you are crossing the event horizon now. For a large black hole, a supermassive one weighing millions or billions of solar masses, crossing the event horizon would feel like nothing. You would pass through it in finite time. Your watch would keep ticking normally. You would not feel a jolt or see a flash. You would not know you had crossed until you tried to turn around and realized you could not. This is one of the strangest features of black holes. The horizon is a point of no return, but it is not a place. It is not a surface you can touch. It is a boundary in space-time that only reveals itself by what it does to trajectories. Once you are inside, every possible future path you could take leads toward the singularity. Not because something is pulling you, but because the geometry of space-time inside the horizon is such that the singularity lies in your future the way next Tuesday lies in your future. You cannot avoid next Tuesday by walking in a different direction. You cannot avoid the singularity by pointing your rocket a different way. It is not a place you are moving toward. It is a moment in time you are moving into. Outside the event horizon, the singularity is a place. A point in space at the center of the black hole. Inside the event horizon, the singularity is a moment. It is in your future, unavoidable, the same way your eventual death is unavoidable. You are not traveling toward it through space. You are traveling toward it through time. This is what general relativity tells us happens. Whether the math is describing reality at that point is an open question, because no one has ever crossed an event horizon and reported back. By definition, they cannot. Which brings us to the information paradox. Information, in the physics sense, is not just facts and figures. It is the complete quantum state of a system. Every particle, every field, every degree of freedom that describes what something is and what it is doing. According to quantum mechanics, information is never destroyed. It can be scrambled, it can be hidden, it can be spread out over a large volume. But the total information content of a closed system is conserved. If you burn a book, the information in that book is not destroyed. It is converted into heat and light and ash, and in principle, if you knew the exact quantum state of every particle in the smoke and the flames and the ashes, you could reconstruct what the book said. In practice, this is impossible, but in principle, the information is still there. Black holes break that rule, or seem to. When something falls past the event horizon, the information describing that object disappears from the observable universe. It is gone. You cannot retrieve it. You cannot reconstruct it. You cannot even know what it was unless you were watching when it fell in. Once it crosses the horizon, it is as if it never existed. The black hole itself does not care what fell in. A black hole has only three properties that can be measured from the outside: its mass, its electric charge, and its angular momentum, meaning how fast it is spinning. That is it. Every other detail is erased. You can throw in a grand piano, or a pile of hydrogen atoms, or a spacecraft full of encyclopedias, And as long as the total mass, charge, and spin are the same, the resulting black hole is identical. John Wheeler, a physicist who spent much of his career thinking about black holes, summarized this with a phrase: "Black holes have no hair," meaning they have no distinguishing features, no information about what fell in is preserved on the outside. But quantum mechanics says information cannot be destroyed. General relativity says it disappears past the event horizon. Those two statements are in direct conflict. That conflict is the information paradox. Stephen Hawking made it worse in the 1970s when he showed that black holes are not entirely black. They emit radiation. This was a shock. According to classical general relativity, nothing can escape from inside the event horizon. Hawking demonstrated that when you account for quantum effects near the horizon, black holes glow, faintly. The radiation is thermal, meaning it has no structure, no information content. It is just random heat. Over an enormously long time, a black hole will radiate away all of its mass and evaporate completely. For a stellar mass black hole, this process takes far longer than the current age of the universe. For a supermassive black hole, it takes incomprehensibly longer, but in principle it happens. When the black hole finally evaporates, what happens to the information that fell in? If the radiation carries no information and the black hole disappears, then the information is gone, destroyed. Quantum mechanics says that cannot happen. The paradox has not been fully resolved. There are ideas. Some physicists think the information is encoded in the Hawking radiation in a way we do not yet understand. Others think it is stored somehow on the event horizon itself, smeared across the surface in a holographic form. Others think the paradox points to a deeper problem with how we understand quantum gravity, and that the resolution will require a theory that unifies general relativity and quantum mechanics. We do not have that theory yet. For now, the paradox stands. The event horizon hides information. Whether it destroys it or just locks it away is one of the biggest unanswered questions in theoretical physics. What we do know is that the event horizon is real. It is not speculation. It is a prediction of general relativity that has been tested extensively. We cannot see an event horizon directly because by definition it emits no light, but we can see the effects. We can watch matter spiral inward and vanish. We can measure the orbits of stars around supermassive black holes and calculate where the event horizon must be. We have even, as of 2019, taken a picture of the shadow cast by an event horizon. That image, produced by the Event Horizon Telescope collaboration, showed the supermassive black hole at the center of the galaxy Messier 87. The black hole itself, the event horizon, appears as a dark circle. Around it, a bright ring of light. That light is coming from the accretion disk, the superhot material swirling just outside the horizon. The dark circle in the middle is not the black hole. It is the shadow, the region where light has been captured and pulled inward. The size of that shadow matches the predictions of general relativity almost exactly. The event horizon is where the predictions say it should be. For a rotating black hole, and most black holes rotate, the situation gets more complicated. The event horizon is no longer a perfect sphere. It bulges slightly at the equator and flattens at the poles. And there is a second boundary outside the event horizon, called the ergosphere. Inside the ergosphere, space-time itself is dragged around by the black hole's rotation. You cannot stand still in the ergosphere. Even if you fire your rockets, space-time is rotating beneath you, and you are carried along with it. You can still escape from the ergosphere. It is outside the event horizon, but you cannot remain stationary. The event horizon of a rotating black hole is described by a different solution to Einstein's equations, derived by Roy Kerr in 1963. The Kerr solution includes effects that do not show up in the non-rotating case: frame dragging, the twisting of spacetime, and the possibility, at least mathematically, of bizarre structures like closed time-like curves, paths through spacetime that loop back on themselves. Whether those structures are physically real or just mathematical artifacts is unknown. We have never observed one. The outer event horizon of a Kerr black hole is still a point of no return. Cross it and you cannot escape. But inside, there is a second horizon, called the inner horizon. And beyond that, the equations predict strange things, regions where time and space swap roles again, paths that might, in principle, lead to other universes or other regions of spacetime. None of this has been confirmed. It may be that the inner horizon is unstable, that quantum effects or in falling matter disrupt it before anything truly weird happens. Or it may be that general relativity is simply not the right tool to describe what happens in those extreme regimes. We do not know. What we do know is that the outer event horizon, the boundary where escape velocity equals the speed of light, is robust. It is the defining feature of a black hole. It is the reason black holes are black. It is the reason they are invisible except by the light of material falling toward them. And it is the reason that anything crossing it is lost to us forever. No signal from inside can reach us. No information can be transmitted outward. No rescue is possible. You can send a probe across the horizon, but you will never hear from it again. Its telemetry will cut off. Its transmissions will redshift into silence. From your perspective, it will hover at the edge, fading until it is gone. From the probe's perspective, it will cross smoothly and continue inward, sending signals that will never arrive. The event horizon is a one-way door built from warped spacetime. It is not a physical object. It is a consequence of how mass bends the fabric of the universe when that mass is compressed into a small enough volume. And it exists not in some distant hypothetical corner of the cosmos, but right here in our galaxy. 100 million stellar mass black holes scattered through the Milky Way, each one carrying an event horizon with it, silent, invisible, waiting. The nearest known black hole to Earth sits about 1,500 light-years away, a safe distance, but not an unreachable one. Someday, if humanity lasts long enough and builds the right technology, we will send something close to an event horizon, close enough to measure, close enough to test the predictions, close enough to see directly what happens at the boundary where the universe closes its doors. Until then, we watch from a distance. We measure the orbits of stars around invisible companions. We map the X-rays from accretion disks. We photograph the shadows cast by horizons millions of light-years away. And at the center of our own galaxy, 26,000 light-years from the chair you are sitting in, there is a supermassive black hole weighing 4 million times the mass of the Sun. Its event horizon spans about 24 million kilometers, larger than the orbit of Mercury, smaller than the orbit of Venus. And every 11.5 years, a star called S2 swings past it at a distance so close that relativistic effects become measurable. We have been watching that star for decades, mapping its orbit, timing its motion, using it as a probe to test general relativity in the strongest gravitational field we can observe. That black hole has a name, Sagittarius A star, and it is the closest thing we have to a laboratory for studying event horizons in the real universe. We ended at the edge of our own galaxy's gravitational well. 26,000 light-years from the chair you are sitting in, buried behind curtains of dust and gas so thick that no optical telescope will ever see it directly. There is a monster. It weighs 4 million times the mass of our Sun. Its event horizon spans about 12 million kilometers, roughly the distance from Earth to the Sun, edge to edge. It is invisible, it is silent, and every star in the Milky Way, all 400 billion of them, is moving in response to its gravity. Its name is Sagittarius A star. Astronomers abbreviate it SCR A star, and the star part of the name is a historical accident. When radio astronomers first detected a bright radio source at the center of the galaxy in the 1970s, they assumed they were looking at something stellar. A compact object, sure, but a star nonetheless. They named it accordingly. By the time they realized what they were actually looking at, the name had stuck. We are still calling it Sagittarius A star, even though it is not a star. It is a black hole, the supermassive kind. The kind that sits at the center of galaxies and quietly dominates everything within a few thousand light years. For most of the 20th century, the idea that black holes existed at all was controversial. The idea that gigantic ones weighing millions of solar masses sat at the centers of galaxies was considered speculative at best, science fiction at worst. Then astronomers started measuring things. They pointed radio telescopes at the centers of distant galaxies and found compact, incredibly bright sources of radiation. They pointed optical telescopes at those same regions and found stars moving at absurd speeds, orbiting something they could not see. They ran the numbers, and the only explanation that fit was a concentrated mass so large that nothing else made sense. Not a dense cluster of stars, not a cloud of dark matter, a black hole. By the 1990s, the evidence was overwhelming. Nearly every large galaxy observed had something massive and dark sitting at its core. The Milky Way, it turned out, was no exception. Astronomers had been watching the galactic center for decades, mapping the radio emissions, tracking infrared sources, trying to figure out what was going on in that crowded, violent region. And in the middle of it all, right at the dynamical center of the galaxy, was SCR A star, a radio source sitting perfectly still while everything around it moved. The breakthrough came from watching the stars. Not the faint background stars scattered across the sky, but the bright ones orbiting close to the galactic center. Stars with names like S2, S62, SO102. Designations that sound like serial numbers because there are dozens of them, all packed into a region smaller than our solar system, all screaming around the center at velocities that should not be possible unless something extraordinarily massive is holding them in place. The observations took decades. You cannot just point a telescope at the center of the galaxy and see what is happening. The galactic center is hidden behind roughly 25 magnitudes of extinction in visible light. That is astronomer speak, for the light is blocked by so much dust that for every trillion photons emitted, only one gets through. You could aim the Hubble Space Telescope at SCR A star for a year and see nothing. The dust clouds are too thick, the visible light is gone, infrared gets through, not all of it, but enough. Dust absorbs and scatters short wavelengths, blue and green and ultraviolet, but it lets the longer wavelengths pass. Infrared light, the kind emitted by warm objects, by stars whose light has been reddened by distance or by gas that is merely hot instead of blindingly bright, makes it through the dust. Build an infrared telescope, mount it on a mountain where the atmosphere is thin and dry, and you can see through to the center. Two teams did exactly that, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, the other led by Andrea Ghez at UCLA. Both teams started observing the galactic center in the early 1990s using adaptive optics, a technology that corrects for the blurring caused by Earth's atmosphere in real time. They mapped the stars near Sagittarius A star. They tracked their positions year after year. And slowly, orbit by orbit, they watched those stars move. The star that made the case airtight is called S2. It orbits Sagittarius A star once every 16 years. Its orbit is highly elliptical, meaning it swings very close to the black hole at one point and very far at another. At closest approach, S2 comes within about 17 light-hours of Sagittarius A star. 17 light-hours. That is roughly 4 times the distance from the Sun to Neptune. For a star orbiting the center of the galaxy, that is absurdly close. And at that distance, it is moving at almost 5,000 kilometers per second. That is 1.5% of the speed of light, for an object with mass. A star weighing more than 10 times what our Sun does, hauling itself around a curve at nearly 2% light speed, because the thing it is orbiting is pulling that hard. When you measure an orbit, you can calculate the mass of the object being orbited. This is basic Newtonian gravity. The tighter the orbit and the faster the motion, the more massive the central object has to be. S2's orbit is so tight and so fast that the central object must weigh at least 4 million solar masses, and it must be small. If the mass were spread out over a large volume, say a dense cluster of stars, S2 would be plowing through it. It would be colliding with other stars. Its orbit would be unstable. The fact that S2 has completed multiple orbits without deviation means the mass is concentrated in a region smaller than S2's closest approach, smaller than 17 light-hours. There is only one object in known physics that can pack 4 million solar masses into a region that small, a supermassive black hole. Genzel and Ghez shared the Nobel Prize in Physics in 2020 for proving it, not for theorizing about it, not for suggesting it, for proving it, with 30 years of continuous observations that Sagittarius A star is a black hole weighing approximately 4.3 million solar masses. The current best estimate, published in 2022, puts the mass at 4.297 million solar masses, plus or minus about 12,000 solar masses. The uncertainty is smaller than the mass of a single star. That is the precision we are working with now. We know how heavy the black hole at the center of our galaxy is to within a fraction of a percent. We know where it is. We know it is not moving. And we know, because dozens of stars are orbiting it in ways that match the predictions of general relativity almost exactly, that it is a black hole. What we do not entirely know is why it is there, or more precisely, how it got there. Supermassive black holes are common. Virtually every large galaxy we have observed contains one. Some weigh millions of solar masses, some weigh billions. A few weigh tens of billions. The black hole at the center of the galaxy Messier 87, the one photographed by the Event Horizon Telescope in 2019, weighs about 6.5 billion solar masses. The black hole in the quasar Tone 618, one of the most massive ever measured, weighs around 66 billion solar masses. Sagittarius A star is a lightweight by comparison. 4 million solar masses is small for a supermassive black hole. But even a small supermassive black hole is a problem if you are trying to explain how it formed. Stellar mass black holes, the kind formed from collapsing stars, weigh a few to a few dozen solar masses. Growing one of those into a 4 million solar mass monster takes time, a lot of time. Black holes grow by accreting matter, pulling in gas and dust, and occasionally entire stars, or by merging with other black holes. Both processes are slow. There is a limit to how fast a black hole can accrete matter, called the Eddington limit, set by the fact that in falling matter heats up and emits radiation, and that radiation pushes back on the surrounding gas, choking off the inflow. Accrete faster than the Eddington limit allows, and you blow away your own fuel supply. Even at the Eddington limit, a stellar mass black hole doubles its mass only every few tens of millions of years. Start with a 10 solar mass black hole formed from a collapsing star, and grow it at maximum speed for the entire 13.8 billion year history of the universe, and you still do not get to 4 million solar masses. You might get to a few 100,000, maybe a million if everything goes perfectly, but not 4 million. Not unless the black holes started much larger than a stellar remnant, or unless the growth rate in the early universe was much faster than current models predict, or unless supermassive black holes formed by a completely different mechanism that we do not fully understand. The leading idea is called direct collapse. In the chaotic early universe, less than a billion years after the Big Bang, enormous clouds of primordial gas could have collapsed directly into black holes weighing hundreds of thousands of solar masses without ever forming stars first. If you start with a seed that large, growing to 4 million solar masses becomes plausible. You still need billions of years and a steady supply of gas, but the timeline works. The problem is that we have never observed a direct collapse black hole in the process of forming. We have seen the end products, supermassive black holes sitting in galaxies billions of light years away, but we do not know for certain how they started. Another possibility is runaway mergers. In the dense cores of early galaxies, where stars formed rapidly and collisions were common, black holes could have merged repeatedly, each merger adding mass and kicking the growing black hole into a higher weight class. Do that enough times in quick enough succession, and you could build a supermassive black hole in less than a billion years. This mechanism probably happens. We have detected gravitational waves from merging black holes dozens of times now, thanks to LIGO and Virgo. But all of those mergers involved stellar mass black holes, tens of solar masses at most. Scaling up to millions of solar masses requires a lot of mergers, and it is not clear whether the early universe provided the right conditions for that to happen fast enough. A third idea is that primordial black holes formed in the first fractions of a second after the Big Bang from quantum fluctuations in the density of space itself could have served as seeds. These would not have formed from collapsing stars or gas clouds. They would have been born directly from the structure of the early universe, and they could have had any mass, from microscopic to millions of solar masses. If primordial black holes exist, and if some of them were large, they could explain supermassive black holes without requiring any exotic growth mechanisms. The downside is that we have no direct evidence that primordial black holes exist at all. What we do know is that supermassive black holes showed up early. We have found quasars, the active feeding phases of supermassive black holes, in galaxies that formed less than a billion years after the Big Bang. The universe at that point was an infant. The first stars had only recently ignited. Galaxies were still assembling. And yet there were already black holes weighing millions or billions of solar masses, shining brighter than anything else in the cosmos. However they formed, it happened fast. Too fast, according to some models, which means either the models are incomplete or there is physics we are missing. Scar A star, sitting at the center of the Milky Way, is quieter than most of its peers. It is not actively feeding. It is not a quasar. It does not have jets of plasma screaming out of its poles at relativistic speeds. It is, by the standards of supermassive black holes, calm, dormant, almost boring. Most of the time, Scar A star just sits there, a dark gravitational anchor at the center of the galaxy, doing nothing. Occasionally, a gas cloud drifts too close. Occasionally, a star wanders into the inner region and gets torn apart. When that happens, the black hole brightens. The infalling material heats up, emits X-rays, and for a few hours or days, Sagittarius A star flares. Then it fades back to its baseline glow, and the region goes quiet again. That calmness is unusual. Many supermassive black holes, especially in distant galaxies, are violently active. They are surrounded by enormous accretion disks, swirling structures of gas and dust that spiral inward over millions of years, heating to millions of degrees as they fall. The radiation from these disks is so intense that it can outshine the entire galaxy. In some cases, magnetic fields threading through the accretion disk launch jets of material outward at nearly the speed of light. Those jets can extend for hundreds of thousands of light years, carving tunnels through intergalactic space, visible across billions of light years as bright radio sources. Sagittarius A star does none of that. It has no major accretion disk, no jets, no sustained radiation. The galactic center is relatively empty of gas. Whatever fuel was available has either been consumed already or blown away by earlier bursts of activity. What is left is a black hole sitting in the middle of a galaxy that has mostly settled down. Stars orbit it. Gas clouds drift past occasionally. But there is no ongoing feast, no continuous infall. Sagittarius A star is between meals. That does not mean it is unimportant. Supermassive black holes, even quiet ones, play a critical role in galactic evolution. The energy released during their active phases, when they were feeding heavily billions of years ago, shaped the galaxies around them. Radiation from the accretion disk heats surrounding gas, preventing it from collapsing into stars. Jets plow through the interstellar medium, pushing gas out of the galaxy entirely. The result is a feedback loop. The black hole grows by eating gas. The energy released by that growth heats and expels more gas. Eventually, the black hole runs out of fuel and the growth stops. The galaxy settles into a quieter state. Star formation slows. The black hole, now massive and dormant, sits at the center, its gravitational influence extending across thousands of light years, keeping the core of the galaxy stable. Without supermassive black holes, galaxies would look different. Star formation rates would be higher. Galaxy cores would be denser. The distribution of gas and stars would follow different patterns. Supermassive black holes are not just passengers in galaxies, they are architects, shapers of structure, regulators of growth. Sagittarius A star, sitting dormant at the center of the Milky Way, has shaped the history of this galaxy in ways we are only beginning to understand. The region immediately around Sagittarius A star is one of the strangest environments in the galaxy. It is called the central parsec. A parsec is about 3 light years, so the central parsec is a sphere 6 light years across, with the black hole at its center. Inside that sphere, stellar densities are millions of times higher than in the solar neighborhood. Stars are packed so tightly that close encounters and collisions happen regularly. The gravitational field is so strong that stars on tight orbits experience measurable relativistic effects. Time dilation, orbital precession, gravitational redshift. All the exotic predictions of general relativity that are barely noticeable in the solar system become obvious near Sagittarius A star. The star S2, the one that proved the black hole's mass, has an orbit so elliptical that at closest approach it experiences gravitational redshift strong enough to measure. Light climbing out of the gravitational well loses energy, its wavelength stretches. The effect is tiny, a shift of about 200 kilometers per second in the star's apparent velocity. but it is real. Astronomers detected it in 2018, another confirmation that general relativity works exactly as predicted, even in the most extreme gravitational environments we can observe. There are stars orbiting even closer. S62 completes an orbit in less than 10 years. So 102 swings past at a distance of just 12 light hours, closer than any other known star. These objects are laboratories for testing gravity in regimes we cannot replicate anywhere else. Every orbit provides another data point. Every closest approach tests whether general relativity still holds. So far, it does. Every measurement matches the predictions. The black hole behaves exactly as the equations say it should. The long-term monitoring of Sagittarius A has also revealed something unexpected. The black hole wobbles, not the black hole itself. The apparent position of Sagittarius A shifts slightly over time because the black hole is orbited by something we cannot see. The wobble is tiny but measurable. The most likely explanation is that there is an intermediate mass black hole, weighing a few thousand solar masses, orbiting Sagittarius A at a distance of a few light months. If confirmed, this would be the first detected intermediate mass black hole in the galaxy, filling in a missing link between stellar mass and supermassive black holes. The data is still preliminary. More observations are needed. But the possibility is tantalizing. Sagittarius A is not just a passive object sitting at the center of the galaxy. It is an active participant in the dynamics of the galactic core. Its gravity shapes the orbits of nearby stars. Its occasional flares inject energy into the surrounding medium. And its presence, dominating the central region with a mass equivalent to 4 million suns compressed into a volume smaller than the inner solar system, makes the galactic center one of the most extreme environments in the Milky Way. The Event Horizon Telescope imaged Sagittarius A in 2022, 3 years after imaging the black hole in Messier 87. The image shows the same basic structure. A dark central region, the shadow of the event horizon, surrounded by a bright ring of emission from the accretion disk. The ring is not uniform. There are bright spots, regions where gas is hotter or denser, moving at different speeds, creating a lopsided, flickering glow. The image is lower resolution than the Messier 87 image because Sagittarius A is smaller and the gas around it is more turbulent, changing on timescales of minutes. But the shadow is there. The event horizon is where general relativity predicts it should be. The radius matches the calculated Schwarzschild radius for a black hole of 4 million solar masses, almost exactly. That shadow is 12 million kilometers across. If you placed it at the center of the solar system, the event horizon would fit comfortably inside the orbit of Mercury. The black hole itself, the singularity at the center, is smaller still. Infinitely small, according to general relativity, though most physicists suspect quantum gravity effects prevent true singularities from forming. We do not know. The singularity is hidden behind the event horizon. We cannot see it. We cannot measure it directly. We can only infer its existence from the geometry of space-time around it. But the event horizon is real, visible, measurable, photographed, sitting 26,000 light-years away at the center of the galaxy, anchoring 400 billion stars in a slow gravitational dance that has been playing out for more than 13 billion years. And every star in that dance, including ours, is moving in response to Sagittarius A's pull. Not directly. The Sun is too far away for Sagittarius A to exert any noticeable tidal force. But the overall structure of the galaxy, the distribution of mass, the shape of the spiral arms, the motion of the galactic disk, all of it is influenced by the fact that there is a 4 million solar mass black hole sitting in the middle, holding the core together. The black hole does not control the galaxy. It is not pulling stars inward. Most of the galaxy's mass is in stars and dark matter distributed across 100,000 light-years. Sagittarius A star contributes only a tiny fraction of the total, but in the central region, within a few thousand light-years of the core, the black hole dominates. It sets the pace. It defines the structure. And anything that ventures too close finds itself in an environment where the normal rules start bending, where space-time curves sharply, where gravity pulls not just on objects, but on light, on time, on the very geometry of existence. Get close enough to Sagittarius A star, and the tidal forces become noticeable, not catastrophic yet, not at a few light-years out, but present, measurable, acting on anything with size, with structure, with parts that can be pulled in different directions. Stars orbiting in the central parsec do not feel those forces strongly, because stars are held together by their own gravity. But smaller objects, objects without enough self-gravity to resist, would start to stretch. A spacecraft, a planet, an asteroid. Anything that ventured too close would find that the side facing the black hole was being pulled harder than the side facing away. The difference in gravitational force across the object's diameter would begin to deform it, elongating it, stretching it in the direction of the black hole while compressing it perpendicular to that direction. Physicists call this spaghettification. And closer in, much closer, near the event horizon itself, the tidal forces become so extreme that no known material can withstand them. Molecular bonds break. Atomic structures fail. Matter is pulled apart into streams of individual atoms, then subatomic particles, spiraling inward toward the singularity in thin threads like noodles. It is not a pleasant process. It is not survivable. And it is what happens to anything that crosses the event horizon of a black hole without sufficient size or structural integrity to resist. We left Sagittarius A star sitting quietly at the center of the Milky Way, a 4 million solar mass black hole dominating the galactic core with its gravity. We talked about its event horizon, that 12 million kilometer boundary where escape velocity equals the speed of light. We described it as a point of no return, a one-way door built from warped spacetime. But we have not yet confronted what happens to you if you approach that door. What happens to matter, to structure, to the integrity of anything with size when it ventures too close to a black hole? The short answer is that it gets torn apart. The longer answer involves tidal forces, molecular bonds breaking under strain, and a process with one of the most darkly poetic names in all of physics, spaghettification. Tidal forces are not unique to black holes. They exist anywhere there is a gravitational gradient, which is to say, everywhere. You are experiencing tidal forces right now. The moon pulls on Earth, and that pull is stronger on the side of Earth facing the moon than on the side facing away. The difference in gravitational force across Earth's diameter creates a slight stretching effect. The oceans respond by bulging outward on both sides, toward the moon and away from it. We call those bulges tides. The same thing happens with the sun, though the effect is weaker because the sun is farther away. Combine the two and you get spring tides and neap tides, the regular rise and fall of sea level that has shaped coastlines and human activity for as long as there have been coastlines and humans. The key point is that tidal forces arise from differences in gravitational pull across a distance. Gravity weakens with distance. The side of an object closer to a massive body feels a stronger pull than the side farther away. For most situations we encounter in daily life, that difference is negligible. The tidal force acting on your body right now, due to Earth's gravity, is effectively zero. Your feet are slightly closer to the center of the Earth than your head, so in principle they are being pulled slightly harder. In practice, the difference is so tiny that your body does not notice. The structural integrity of bone and tissue is more than enough to resist any stretching. Scale that up. Put yourself in orbit around a more massive object, or move closer to an existing one, and the gradient steepens. The difference in gravitational pull between your head and feet increases. At some point, the difference becomes noticeable, then uncomfortable, then structural, then catastrophic. The object you are orbiting does not have to be exotic. Get close enough to any massive body and tidal forces will tear you apart. Jupiter could do it. The Sun could do it. Get within a few thousand kilometers of a neutron star and the tidal forces would rip apart a spacecraft, then rip apart the atoms that made up the spacecraft, long before you hit the surface. Black holes make tidal forces extreme because they pack enormous mass into a tiny volume. The gravitational gradient near a black hole is steeper than anywhere else in the universe. The difference in pull between one side of an object and the other can exceed the strength of any known material. Molecular bonds, atomic forces, the electromagnetic interactions that hold matter together, all of it fails when the tidal gradient gets strong enough. The object stretches. It elongates in the direction of the black hole while compressing perpendicular to that direction. If the object has any internal structure, any parts that were not originally aligned in a straight line toward the black hole, those parts get pulled into alignment. The object becomes a thin stream of matter, elongated like a noodle, spiraling inward, hence the term spaghettification. The process by which tidal forces stretch an object into a long, thin strand. The term was popularized by Stephen Hawking in his book, A Brief History of Time, though the concept was understood long before that. Physicists also call it the noodle effect, though that never caught on as widely. Spaghettification sounds absurd, almost comical, but the process it describes is anything but. It is one of the most violent things that can happen to matter. Here is what would happen to a human body falling feet first toward a black hole. We will start far away, where tidal forces are negligible, and work our way inward. At a safe distance, you feel nothing unusual. You are in free fall, weightless, drifting toward the black hole at whatever velocity you started with. Gravity is pulling you inward, yes, but you are not being compressed or stretched. You are simply falling. This is what astronauts on the International Space Station experience: free fall. The sensation of floating. Gravity is acting on you, but because every part of your body is accelerating at the same rate, you do not feel it. As you get closer, the gravitational field strengthens. Your velocity increases. Still, nothing unusual. You are falling faster, but you still feel weightless. Free fall does not change just because you are accelerating. Then, at some distance that depends on the mass of the black hole, the tidal gradient becomes noticeable. Your feet, which are closer to the black hole than your head, start being pulled harder. Not much harder, not yet. Just enough that you can feel it. A slight tugging sensation, a sense that your body is being gently stretched. It is not painful. Not at this stage, just odd. You are still intact, still conscious, still capable of thought, but something is happening that does not happen in normal life. Move closer and the sensation intensifies, the pull on your feet strengthens. The difference in gravitational force between your feet and your head grows. Your spine begins to stretch, not dramatically, not yet, but noticeably. You are being elongated. At the same time, you are being compressed from the sides. Tidal forces do not just stretch, they squeeze. The reason is geometry. Gravitational field lines converge toward the center of the black hole. As you fall inward, those field lines are pulling you not just down, but inward from all sides. Your body is being elongated along the direction of fall and compressed perpendicular to it. You are being turned into a cylinder, then a rod, then a thread. At some point, the forces exceed what your body can withstand. Tissue begins to tear, bones begin to fracture, blood vessels rupture. The process is not uniform. Your feet, experiencing the strongest pull, go first. The bones in your feet crack, the ligaments snap, the skin stretches and splits. Your legs follow, then your torso, then your head. You are being pulled apart from the bottom up, one layer at a time, like a piece of taffy stretched too far. The pain, assuming you are still conscious to feel it, would be extraordinary. But consciousness would not last long. Blood flow to the brain depends on pressure gradients that make sense in normal gravity. In a tidal field strong enough to tear your body apart, your cardiovascular system fails almost immediately. Long before you cross the event horizon, you are dead. Your body has been reduced to a stream of disconnected tissue, bone fragments, and organic molecules, all stretched into a thin line, all falling inward at slightly different rates, because the parts that were closer to the black hole are still being pulled harder than the parts that were farther away. What remains is no longer recognizable as human. It is a column of biological material, a few meters long, a few centimeters wide, spiraling toward the event horizon in a trajectory that will never reverse. This is spaghettification, not a quick death, not a clean one. A drawn-out disintegration caused by the fact that gravity pulls harder on one part of you than another, and the difference is strong enough to overcome the forces holding you together. Neil deGrasse Tyson once described it as being extruded through the fabric of space like toothpaste through a tube. That image is visceral, and it is accurate. You are not crushed, you are stretched, pulled, elongated until the integrity of your structure fails, and you become a stream of matter defined more by the gravitational field acting on you than by any property you used to have. The distance at which this happens depends entirely on the mass of the black hole. For a stellar mass black hole, the kind formed from a collapsed star, weighing maybe 10 times the mass of the Sun, the tidal forces at the event horizon are catastrophic. A human body would be torn apart well before reaching the horizon. Estimates vary, but a commonly cited figure suggests that for a black hole of 1 solar mass, a human would experience lethal tidal forces at a distance of around 700 kilometers from the center. That is outside the event horizon by a significant margin. For a 10 solar mass black hole, the event horizon sits at about 30 kilometers. The lethal tidal distance would be farther out, maybe a few hundred kilometers. You die long before you cross. This is counterintuitive. You might expect the event horizon to be the dangerous part, the boundary where things go wrong, but the event horizon is just a mathematical surface. It is the point where escape velocity equals the speed of light. It says nothing about tidal forces. Tidal forces depend on the curvature of space-time, and curvature depends on how much mass is packed into how much space. For a small black hole, the curvature near the event horizon is extreme. The gravitational gradient is steep. Tidal forces are enormous. For a large black hole, the curvature is gentler. The event horizon is farther from the center, and the gradient at that distance is less steep. Tidal forces are weaker. This leads to one of the strangest facts about black holes. The bigger the black hole, the safer it is to cross the event horizon. Supermassive black holes, the kind weighing millions or billions of solar masses, have event horizons so large that the tidal forces at the horizon are negligible. A human could cross the event horizon of a supermassive black hole and not feel anything unusual. No stretching, no tearing, no pain. You would pass through the boundary smoothly, still intact, still conscious, with no indication that you had just crossed the point of no return. From your perspective, nothing would change. You would look around and see stars, light, the universe you left behind, all still visible, though increasingly redshifted and distorted. You would not realize you were doomed until you tried to turn around and discovered you could not. Every direction you could point yourself, every thrust you could fire, would lead further inward. Outward would no longer exist as an option. You would still be alive, still whole. But your future would now contain only one event, the singularity. And as you continued falling, the tidal forces would eventually catch up with you. Even in a supermassive black hole, the tidal gradient increases as you approach the center. Closer in, much closer, the forces would strengthen. Your body would begin to stretch. The process would play out the same way it does near a stellar mass black hole, just delayed. By the time the stretching started, you would already be inside the event horizon, already cut off from the outside universe, already beyond any possibility of rescue or escape. For Sagittarius A star, the supermassive black hole at the center of the Milky Way, the event horizon has a radius of about 12 million kilometers. The tidal forces at that distance are weak. A spacecraft could cross the horizon without structural damage. A human could cross it and survive, at least initially, but continue inward, and eventually the tidal gradient steepens. At some distance inside the horizon, closer to the singularity, the forces would become lethal. The body would stretch, the process would begin, and there would be no way to stop it, because by that point, the singularity is not a place you are moving toward. It is a moment in time you are moving into. Inevitable, unavoidable, written into the geometry of space-time itself. The threshold where tidal forces become lethal is sometimes called the spaghettification radius. For a stellar mass black hole, it lies outside the event horizon. For a supermassive black hole, it lies inside. The distinction matters because it changes what an outside observer can see. If spaghettification happens outside the horizon, the process is visible. Light from the disintegrating object can still escape. Telescopes can, in principle, watch it happen. If spaghettification happens inside the horizon, it is hidden. No light escapes. The event is sealed off from the rest of the universe. Astronomers have observed tidal disruption events, instances where black holes tear apart stars. The process is similar to spaghettification, but scaled up. A star, held together by its own gravity, wanders too close to a supermassive black hole. The tidal forces acting on the star exceed the star's self-gravity. The near side of the star is pulled harder than the far side. The star stretches, it elongates, the structure fails. The star is ripped apart into streams of gas that spiral inward, heating up as they fall, emitting enormous amounts of light and X-rays. The brightening can be seen across millions of light years. The flare lasts weeks or months as the debris continues to fall in, then fades as the last of the material crosses the event horizon. These events are rare. A given galaxy might experience one every 10,000 to 100,000 years. But the universe contains billions of galaxies, so tidal disruption events are happening somewhere all the time. Astronomers have catalogued dozens of them. Each one is a real-time demonstration of tidal forces at work. A star, intact one moment, shredded the next, because it ventured too close to an object whose gravitational gradient was too steep to survive. The forces involved are almost incomprehensible. A paper published in 2022 calculated that near a stellar mass black hole, the tidal force acting on a human body could reach thousands of Earth gravities. Not the total gravitational pull, which would be far higher, but the difference in pull between head and feet. Thousands of times the force that holds you to the ground right now, acting not to pull you down but to stretch you apart. No material can withstand that. Steel would fail, diamond would fail. Atomic nuclei, held together by the strong nuclear force, one of the most powerful forces in physics, would eventually fail if the tidal gradient grew strong enough. Matter itself has limits. Push it past those limits and structure collapses. The practical threshold for a human body is much lower. Estimates suggest that a difference of around 2,000 pounds of force, roughly 9,000 newtons, between head and feet is enough to cause fatal injuries. Tissue tears, blood vessels rupture, the spine dislocates. This is not even close to the maximum tidal force near a black hole. This is just the point where the human body stops functioning. Spaghettification, the complete disintegration into a thin stream, requires forces far beyond that. Forces strong enough to overcome the molecular bonds holding tissue together, to pull apart the proteins and lipids and carbohydrates that make up cells, to separate molecules into individual atoms. Once you are spaghettified, the process does not stop. The atoms themselves continue falling. And as they get closer to the singularity, the tidal forces continue to increase. At some point, the forces become strong enough to affect atomic structure. Electrons are stripped away, atoms are ionized. Then the nuclei themselves begin to feel the strain. Protons and neutrons, held together by the strong force, are pulled apart. Quarks, the fundamental particles that make up protons and neutrons, are separated. At the singularity, if general relativity is correct, the tidal forces become infinite. Curvature becomes infinite, density becomes infinite, and everything that falls in is crushed to a point of zero volume. Most physicists do not believe this is what actually happens. Infinite values in physics usually mean the theory has broken down. General relativity, which predicts the singularity, does not account for quantum mechanics. At the scales where singularities would exist, quantum effects should dominate. The true structure of a black hole's core is likely governed by a theory of quantum gravity that we do not yet have. Until we do, the singularity remains a placeholder, a boundary where our equations stop giving meaningful answers and we are forced to admit that we do not know what happens next. But the tidal forces leading up to that boundary are real, measurable, observable, at least indirectly. Spaghettification is not speculation. It is a prediction of general relativity that follows directly from the mathematics of curved spacetime. And while no human will ever experience it, the process happens constantly throughout the universe. Gas clouds fall into black holes and are stretched into thin streams. Stars wander too close and are torn apart. Matter is funneled inward, elongated, compressed, heated, and eventually lost beyond the event horizon. The image of spaghettification has become iconic. It is one of the few aspects of black hole physics that translates easily into something visceral, something the human brain can picture, even if it cannot fully comprehend. You do not need to understand tensor calculus or the Einstein field equations to grasp what it means to be stretched until you break. The concept is immediate, terrifying, and entirely accurate. It also highlights one of the deep truths about black holes. They are not just objects with strong gravity. They are regions where the rules governing structure and integrity stop applying, where the forces holding matter together, forces that are nearly absolute everywhere else in the universe, become irrelevant, where the geometry of spacetime itself becomes the dominant feature, warping everything that comes near into shapes dictated purely by gravitational gradients. You cannot armor against spaghettification. You cannot build a material strong enough to resist it. Once the tidal gradient exceeds the strength of atomic bonds, structure fails. The object, whatever it was, becomes a stream of particles defined by the trajectory they follow and nothing else. Identity, form, function, all of it is erased. What falls into a black hole stops being what it was and becomes simply mass, energy. Information, if you believe information is conserved, though even that is debated. From the outside, we can watch the process begin. We can see stars being disrupted, gas clouds being stretched, accretion disks forming from material that has not yet crossed the horizon but is already doomed. We can measure the brightening, track the debris, calculate the forces involved. But once the material crosses the event horizon, it disappears from view. The final stages of spaghettification, the moment when atoms are ionized and nuclei are torn apart and matter is reduced to its most fundamental components, all of that happens in a region we cannot observe. It is hidden behind the horizon, sealed off by the geometry of spacetime, lost to us forever. And yet we know it is happening. The mathematics is clear, the predictions are robust. Spaghettification is not optional. It is not something that might happen under certain conditions. It is what happens to anything with spatial extent that falls far enough into a black hole. The only variable is where it happens, outside the horizon for small black holes, inside for large ones. But it happens. This makes black holes unlike any other object in the universe. Stars can be dangerous. Get too close and you burn. Neutron stars have surface gravity so strong that falling a single meter would accelerate you to a significant fraction of the speed of light. White dwarfs are dense enough that a sugar cube of their material would weigh as much as a car. But none of those objects guarantee your destruction by virtue of their geometry alone. You can, in principle, orbit a neutron star safely. You can observe a white dwarf from a distance. You can study a star without being consumed by it. Black holes offer no such safety. Get close enough and you are gone, not because you crashed into something, not because you overheated or were irradiated, but because the structure of spacetime itself, warped beyond recognition, pulled you apart and funneled you inward to a place from which no information, no signal, no trace of what you were can ever return. The event horizon is a warning, a boundary that says beyond this point, the universe stops playing by the rules you are used to. Spaghettification is what happens when you ignore that warning. When you cross the line, when you venture into a region where gravity is no longer a force pulling you towards something, but a curvature so extreme that it dictates the only possible future. Inward, always inward, until there is nothing left of you but a smear of particles falling toward a singularity that may not even exist in the way we think it does. And all of this, the stretching, the tearing, the inevitable disintegration, happens because of a simple fact. Gravity pulls harder on things that are closer. Scale that fact up to a black hole, and the result is spaghettification, a process as unavoidable as it is violent, as predictable as it is final. But we are not done yet, because while we cannot see inside the event horizon, we have managed to photograph the boundary itself. We have taken pictures of event horizons, images of the shadows they cast, proof that these objects, predicted by mathematics, confirmed by observation, feared by imagination, are real, sitting out there in space, waiting. And in 2019, we pointed a telescope the size of the Earth at one of them and captured the first direct image of a black hole's event horizon. That story, the story of how we photographed the invisible, is where we go next. We left off at the edge of destruction, tidal forces strong enough to pull atoms apart, spaghettification. the violent end that awaits anything with size and structure that ventures too close to a black hole. We described the process in detail because it is one of the few aspects of black hole physics that translates cleanly into something the human brain can picture: stretching, breaking, disintegration. But all of that description was based on mathematics, predictions, models built from Einstein's equations that tell us what should happen near an event horizon, even though no one has ever been there to confirm it. For most of the 20th century, black holes existed primarily on paper. They were solutions to equations, theoretical objects that fell out of general relativity when you pushed the math far enough. Physicists could calculate their properties with extraordinary precision: the size of the event horizon, the strength of the gravitational field, the behavior of light in the curved spacetime surrounding them. But calculations are not the same as observations, and for decades there was no way to observe a black hole directly. By definition, they emit no light. They are invisible. The best astronomers could do was infer their existence from indirect effects: stars orbiting invisible companions, X-rays from superheated gas spiraling inward, jets of plasma launched from accretion disks. All of it pointed to black holes. None of it was a picture. Then, on April 10, 2019, at simultaneous press conferences held in Brussels, Santiago, Shanghai, Taipei, Tokyo, and Washington, scientists revealed something that should not have been possible: a photograph of a black hole. Not an artist's rendering, not a simulation. An actual image constructed from real observational data, showing the shadow cast by an event horizon 55 million light-years away. The target was a supermassive black hole sitting at the center of the galaxy Messier 87, catalogued as M87. The black hole itself is called M87 star, and it weighs about 6.5 billion times the mass of the Sun. Its event horizon spans roughly 40 billion kilometers, larger than the orbit of Neptune. If you placed it at the center of our solar system, the event horizon would extend past Pluto. This is not a small object by any reasonable standard, but it is 55 million light-years away. At that distance, the event horizon subtends an angle on the sky of about 40 microarcseconds. That is the angular size of a grapefruit sitting on the Moon as viewed from Earth. No telescope ever built can resolve an object that small. The Hubble Space Telescope, with its 2.4-meter mirror, has a resolution of about 50 milliarseconds in visible light. That is more than 1,000 times too coarse. Even if you built a single optical telescope the size of a football field, it would not be enough. The resolution you need to image a black hole's event horizon is so extreme that it requires a telescope the size of the Earth. So astronomers built one. The Event Horizon Telescope is not a single instrument, it is a network, a coordinated array of radio telescopes scattered across 4 continents, from Hawaii to Arizona to Spain to Chile to the South Pole, all pointed at the same target at the same time, all recording data with atomic clock precision, all acting together as a single virtual telescope with an effective aperture the size of the planet. The technique is called Very Long Baseline Interferometry, and it is one of the most technically demanding observational methods in all of astronomy. Here is how it works. Radio waves are just light with long wavelengths. Visible light has wavelengths of a few hundred nanometers. Radio waves used in astronomy range from millimeters to meters. The Event Horizon Telescope operates at a wavelength of 1.3 millimeters, which corresponds to a frequency of about 230 gigahertz. That is far into the sub-millimeter range, just barely on the edge of what we call radio. Pick that wavelength for a reason. It penetrates the gas and dust surrounding black holes more easily than shorter wavelengths, and it provides the resolution needed to see features on the scale of an event horizon. When you point a single radio telescope at the sky, it collects radio waves from a specific direction. The waves arrive at the telescope's dish, bounce off the surface, and get focused onto a receiver. The receiver measures the strength of the signal and records it. That gives you an image, but the resolution of that image is limited by the size of the dish. The bigger the dish, the finer the details you can resolve. This is why radio telescopes are enormous. The Arecibo Observatory in Puerto Rico, before it collapsed in 2020, had a dish 305 meters across. The 500-meter Aperture Spherical Telescope in China, currently the largest single-dish radio telescope in the world, has a dish 500 meters wide. Even at that size, the resolution is nowhere near good enough to image a black hole's event horizon. Interferometry gets around this limitation by using multiple telescopes. Point two telescopes at the same target and record the signals from both. The radio waves arriving at each telescope are oscillating electromagnetic fields. At any given instant, the wave has a specific phase. If the two telescopes are separated by a distance, the wave arrives at one telescope slightly earlier or later than it arrives at the other. The difference in arrival time creates a phase shift between the two signals. By comparing the signals from both telescopes, you can measure that phase shift with extraordinary precision. The phase shift tells you something about the structure of the radio source you are observing. Specifically, it tells you how the brightness of the source varies on angular scales, comparable to the separation between the telescopes divided by the distance to the source. This is the core idea of interferometry. The farther apart the telescopes, the finer the details you can measure. If you separate two telescopes by a few kilometers, you can resolve structures on the sky that a single dish could never see. Separate them by hundreds or thousands of kilometers, and the resolution improves proportionally. Separate them by the diameter of the Earth, roughly 13,000 kilometers, and you have a telescope with an effective aperture equal to the Earth's diameter. The resolution is determined not by the size of any individual dish, but by the maximum separation between dishes in the array. The trade-off is complexity. You are not actually forming an image in real time the way a camera does. You are recording the signals from each telescope separately, along with extremely precise timestamps, and then combining them later using computers. The process is called correlation. The data from each telescope is stored on hard drives, physically shipped to a central processing facility, and then analyzed by software that reconstructs the interference pattern. From that interference pattern, you can build an image. It is not a photograph in the traditional sense. It is a reconstruction, a computational product derived from raw interferometric data. The Event Horizon Telescope collaboration spent well over a decade preparing for the observations that produced the M87 image. The project involved more than 200 scientists from institutions around the world. The core team included researchers from MIT, Harvard, the University of Arizona, Radboud University in the Netherlands, the Max Planck Institute for Radio Astronomy in Germany, and the National Astronomical Observatory of Japan, among many others. The observing campaign itself took place over a few nights in April 2017, though the data processing and image reconstruction took another 2 years. 8 observatories participated in the 2017 observations. The Atacama Large Millimeter Array in Chile, a collection of 66 dishes that together act as a single enormous telescope. The Atacama Pathfinder Experiment, also in Chile. The IRAM 30-meter telescope in Spain. The James Clerk Maxwell Telescope in Hawaii. The Large Millimeter Telescope in Mexico. the sub-millimeter array in Hawaii, the sub-millimeter telescope in Arizona, and the South Pole telescope in Antarctica. Each site recorded several petabytes of data, that is, several thousand terabytes. The sheer volume of information was so large that it could not be transmitted over the internet. The hard drives were packed into crates and flown to processing centers in the United States and Germany, where specialized supercomputers spent months cross-correlating the signals. Timing is everything in interferometry. The telescopes need to record their signals with nanosecond precision. A nanosecond is 1/1000th of a second. If the timestamps are off by even that tiny amount, the phase information gets scrambled and the image reconstruction fails. To achieve that precision, each telescope in the array is equipped with an atomic clock. These are not ordinary clocks. They are hydrogen maser frequency standards, devices that use the oscillation of hydrogen atoms to define time with extraordinary stability. Drift over the course of a day is measured in picoseconds. The clocks are synchronized before the observing campaign and checked constantly throughout. Weather is another challenge. Sub-millimeter observations require dry conditions. Water vapor in the atmosphere absorbs radio waves at these wavelengths, turning the sky opaque. That is why most of the EHT sites are located in deserts or at high altitudes where the air is thin and dry. The Atacama Desert in Chile, one of the driest places on Earth, Mauna Kea in Hawaii, a dormant volcano rising more than 4,000 meters above sea level. The South Pole, where the air is not just dry, but frozen. Even with ideal locations, the weather has to cooperate. Clouds, humidity, storms, any of it can ruin a night of observing. The 2017 campaign had only a narrow window, a few nights when conditions at all 8 sites were good simultaneously. The team got lucky, the weather held, the data came through. The next challenge was turning that data into an image. This is not straightforward. The Event Horizon Telescope does not observe every possible baseline. A baseline is the separation between 2 telescopes. With 8 telescopes, you get 28 unique baselines, 28 different pairs. Each baseline samples the radio source at a specific spatial frequency. But the full image contains information at all spatial frequencies, not just the ones you measured. The missing information has to be filled in using algorithms. These algorithms are based on assumptions about what natural images look like: smoothness, symmetry, certain statistical properties. Different algorithms make different assumptions, and they can produce slightly different images from the same data. To guard against bias, the EHT collaboration used 4 independent imaging teams, each working with different software and methods. None of the teams knew what the others were producing until the very end. When they finally compared results, all 4 teams had produced images that looked essentially the same. A bright ring of emission, roughly circular, with a dark region in the center. The consistency across methods gave confidence that the image was real, not an artifact of the reconstruction process. The bright ring is not the event horizon. This is important to understand. The event horizon itself emits no light. It is black, invisible. What the EHT image shows is the photon ring, the region just outside the event horizon where light is bent so severely by the black hole's gravity that it orbits the black hole multiple times before either falling in or escaping. The photons making up that ring come from the accretion disk, the swirling structure of superheated gas spiraling inward. Some of those photons are emitted on trajectories that happen to carry them past the event horizon at just the right distance that they loop around once, or twice, or even more times before heading outward toward us. The result is a bright ring of light encircling the black hole. The dark region in the center is called the shadow. It is larger than the event horizon by a factor of about 2.6. The shadow includes not just the event horizon itself, but also the region where any light emitted would be captured by the black hole. Photons emitted inside this region either fall directly into the event horizon or orbit a few times and then fall in. None escape. The boundary of the shadow is determined by the outermost photon orbit, the trajectory where a photon can loop around the black hole exactly once at a constant radius. Any closer and the photon spirals inward. The shadow is the black hole's footprint on the sky. The size of the shadow depends on the black hole's mass. According to general relativity, the shadow radius for a non-rotating black hole is about 2.6 times the Schwarzschild radius, which is itself proportional to the mass. For M87 star, with a mass of 6.5 billion suns, the Schwarzschild radius works out to roughly 19 billion kilometers. Multiply by 2.6 and you get a shadow diameter of about 40 billion kilometers. The EHT measured the shadow diameter from the image and got a value very close to that prediction. Close enough that the agreement was described in press releases as stunning. Jeffrey Bauer, the EHT project scientist, said they were stunned by how well the size of the ring agreed with predictions from Einstein's theory of general relativity. This is not a minor point. General relativity is more than 100 years old. It has been tested extensively in the solar system, in binary pulsar systems, with gravitational wave detectors, and now with direct imaging of an event horizon. Every test so far has confirmed the theory. The M87 image is the most visually striking confirmation to date. The size of the shadow, the shape of the ring, the brightness distribution, all of it matches what the equations predict for a black hole of that mass in that environment. Heino Falke, a researcher at Radboud University who has been working on black hole imaging for decades, admitted that they would have loved to prove Einstein wrong. But, he said, everything they saw fits perfectly the prediction given by general relativity. The image itself became iconic almost immediately. A bright orange ring on a black background, asymmetric, slightly brighter on one side than the other. The asymmetry is real. It is caused by Doppler boosting, a relativistic effect that occurs when material in the accretion disk is moving at a significant fraction of the speed of light. The side of the disk moving toward us appears brighter because the light is blue-shifted and beamed in our direction. The side moving away appears dimmer because the light is red-shifted and beamed away from us. The result is a lopsided ring, brighter on one side, exactly as predicted. The mass estimate derived from the image also matched earlier estimates made from watching stars orbit the black hole. Astronomers had been tracking stars near the center of M87 for years, measuring their velocities, calculating the mass of the object they were orbiting. The number they got was about 6 billion solar masses. The EHT measurement came in at 6.5 billion. The agreement between two completely independent methods was another validation. One method uses the dynamics of stars over years or decades. The other uses the bending of light measured over a few days. Both point to the same answer. The success of the M87 observation opened the door to more. In May 2022, the EHT collaboration released a second image, this time of Sagittarius A star, the supermassive black hole at the center of the Milky Way. Sagittarius A star is much closer than M87 star, only 26,000 light-years away instead of 55 million. But it is also much smaller, weighing 4 million solar masses instead of 6.5 billion. The event horizon is proportionally smaller, and the material around it is more turbulent. The gas swirls around Spaghettification A star on timescales of minutes, changing so fast that the image blurs unless you account for the variability. The EHT observations of Spaghettification A star had to be processed differently, averaging over many snapshots to build a stable image. The result looked remarkably similar to the M87 image: a bright ring, a dark shadow, the same basic structure, confirming that what the EHT was seeing was not unique to one black hole, but a general feature of event horizons. The imaging of Spaghettification A star also strengthened the case that the object at the center of our galaxy is, in fact, a black hole. There had been very little doubt by that point. Decades of observations had made the case overwhelming. But the EHT image removed any remaining ambiguity. The shadow was there. The size matched the predictions. The structure matched the theory. Spaghettification A star is a black hole, and we now have a picture of its event horizon. Both images are landmarks, not just for black hole physics, but for observational astronomy as a whole. They represent the culmination of techniques that have been developed over decades, pushed to their absolute limits, coordinated on a global scale. The Event Horizon Telescope is not a single instrument that someone built and pointed at the sky. It is a collaboration, a network of independent facilities working together, synchronized by atomic clocks, linked by shared scientific goals, producing data that no single telescope could ever collect. And the data itself is strange. If you looked at the raw output from any one of the EHT telescopes, you would see nothing resembling a picture. You would see a time series. Numbers representing the strength and phase of the radio signal as a function of time. Only when you combine the signals from all 8 telescopes, account for the different arrival times, cross-correlate the phases, and feed the result into an imaging algorithm, do you recover something that looks like a photograph. The process is as much mathematics as observation. The image is a reconstruction, a product of interferometry and computation, not a direct recording of light hitting a sensor. That does not make it less real, it makes it more remarkable, because it means astronomers have figured out how to photograph an object that emits no light, sitting 55 million light-years away, by building a telescope the size of the Earth and processing the data with supercomputers. The image is not what your eye would see if you were there. Your eye does not detect radio waves, but it is a faithful representation of the structure of the radio emissions surrounding the black hole, measured with precision, validated by multiple independent methods, and confirmed to match the predictions of general relativity. The implications go beyond just confirming that black holes exist. We already knew they existed. The M87 and Spaghettification A star images tell us that the event horizon is real, that space-time really does curve the way Einstein said it would, that light really does follow the paths predicted by the equations, that the shadow cast by a black hole has the size and shape and brightness distribution that the theory requires. General relativity is not just approximately correct in these extreme environments. It is correct, exactly correct, within the limits of measurement. That is frightening in its own way, because general relativity is a classical theory. It does not include quantum mechanics. It predicts singularities, infinities, regions where the math breaks down. And yet here, near the event horizon, where gravity is stronger than anywhere else in the universe except maybe inside the horizon itself, the theory works perfectly. No deviations, no anomalies, no hints of new physics. Just Einstein's equations doing exactly what they have been doing for over a century, describing the universe with an accuracy that feels almost unreasonable. There is one more image worth mentioning. The first image, the M87 result, was not just scientifically significant, it became culturally iconic. The bright orange ring on the black background appeared on magazine covers, news broadcasts, social media. People who had never heard of very long baseline interferometry recognized the image. It became shorthand for cutting-edge science, for humanity's ability to achieve the seemingly impossible. Katie Booman, a computer scientist who developed some of the imaging algorithms used by the EHT, became briefly famous when a photo of her reacting to the first reconstructed image went viral. She was smiling, hands over her mouth, staring at a laptop screen showing the ring. The photo captured something real. The moment when years of work, decades of preparation, hundreds of people coordinating across continents, all came together into a single image that confirmed what the equations had been saying all along. Black holes are real, event horizons are real, and we can take their picture. The Event Horizon Telescope is still operating. The collaboration continues to observe M87 star and SCR A star, tracking changes over time, refining the measurements, pushing the limits of what interferometry can achieve. Future expansions of the array, adding more telescopes in Africa and Greenland, will improve the resolution further. And there are plans for a next-generation network that would extend into space, using satellites in orbit as additional baselines, effectively building a telescope larger than the Earth. Those observations, if they happen, will probe even closer to the event horizon, possibly imaging the photon ring in enough detail to test general relativity in regimes we have never accessed before. For now, we have two images, M87 star and SCR A star. Two supermassive black holes, one nearby, one distant, both showing the same fundamental structure. A bright ring, a dark shadow, the boundary where space-time curves so sharply that light can no longer escape. The edge of the universe as seen from the outside. And the images are not artists' conceptions or theoretical predictions, they are measurements. Observational data processed into visual form. Proof that the mathematics written down more than 100 years ago by a physicist working in a patent office in Switzerland, using nothing but thought experiments and tensor calculus, accurately describes the most extreme objects in the cosmos. That is the real achievement. Not just that we imaged a black hole, but that when we did, it looked exactly the way Einstein said it would. We left off at the moment humanity captured something impossible. A photograph of an event horizon. Two images, actually. One from the center of the galaxy Messier 87, 55 million light-years away. One from the center of our own galaxy, sitting 26,000 light-years from where you are reading this. Both showed the same basic structure, a bright ring of light surrounding a dark shadow. The shadow was larger than the event horizon itself, but it marked the boundary. The point where space-time curves so sharply that light can no longer escape, the edge of a region where the rules change. Those images were not just pretty pictures, they were confirmations, tests of a theory that has been guiding physics for more than a century. A theory that reimagined gravity not as a force pulling objects together, but as a distortion in the fabric of space and time itself. A theory that predicted black holes decades before anyone found one. A theory written by a man working in a Swiss patent office who had no telescope, no laboratory, no experimental data, just pen and paper and a mind capable of seeing the universe in a way no one had before. His name was Albert Einstein, and the theory is called general relativity. To understand what general relativity actually says, and why it predicts black holes, you need to start with what came before. Newtonian gravity. Isaac Newton published his law of universal gravitation in 1687. It said that every object with mass attracts every other object with mass. The force between them is proportional to the product of their masses and inversely proportional to the square of the distance between them. Double the distance and the force drops by a factor of 4. Halve the distance and the force quadruples. Simple, elegant. And for more than 2 centuries, it worked perfectly. Newton's gravity explained the motion of planets around the sun. It explained the tides. It explained why apples fall from trees and why the moon stays in orbit. It was used to predict the existence of Neptune before anyone had seen it, just by noticing that Uranus was wobbling in a way that suggested another planet was tugging on it. When astronomers pointed telescopes at the calculated position, there Neptune was. Newtonian gravity was not just a theory, it was the theory, verified over and over. Precise, reliable, complete, except it was not. There was a problem with Mercury. The planet Mercury orbits closer to the Sun than any other planet. Its orbit is elliptical, not circular, and like all ellipses, it has a point of closest approach called the perihelion. In Newtonian gravity, if Mercury were the only planet and the Sun were perfectly spherical, the perihelion would stay in the same place forever. The orbit would trace the same ellipse over and over, a closed loop. But Mercury is not the only planet. The gravitational pull of Venus, Earth, Jupiter, and the other planets tugs on Mercury slightly, causing its orbit to shift. The perihelion precesses. It rotates slowly around the Sun, tracing out a shape like a spirograph pattern over thousands of years. Astronomers could calculate how much precession should occur due to the influence of the other planets. They added up all the gravitational tugs, applied Newton's equations, and got a number: 43 arcseconds per century. That is tiny. An arcsecond is 1/3600th of a degree. 43 arcseconds is barely more than 1/100th of a degree per century, but it was measurable. And when astronomers measured Mercury's actual precession, they got a different number. The perihelion was precessing faster than Newton predicted, not by much, by about 43 arcseconds per century, but the discrepancy was real, and no one could explain it. Some astronomers proposed that there was another planet inside Mercury's orbit, tugging on it in just the right way to account for the extra precession. They even gave it a name, Vulcan. Searches were conducted. No planet was found. Others suggested that the Sun was not perfectly spherical, that it bulged at the equator enough to generate the extra pull. Measurements of the Sun's shape ruled that out. The precession remained unexplained. A tiny crack in Newtonian gravity that no one could patch. Then, in 1915, Einstein published the final version of his general theory of relativity. The core idea was radical. Gravity is not a force, it is geometry. Mass and energy do not pull on other objects across empty space. They warp the space and time around them, and objects move through that warped geometry. A planet orbiting the Sun is not being pulled by an invisible force. It is following the straightest possible path through curved spacetime. The Sun's mass bends spacetime, and the planet follows the curve. This was not a minor adjustment to Newton. It was a complete rethinking of what gravity is. In Newton's picture, space is flat and unchanging. Time ticks at the same rate everywhere. Objects move through space in response to forces. In Einstein's picture, space and time are woven together into a single four-dimensional structure called spacetime. That structure is flexible. Mass and energy curve it. The more mass, the more curvature. Objects move through that curved spacetime along paths called geodesics, which are the closest thing to straight lines in a curved space. Einstein's equations, the field equations of general relativity, are fiendishly complicated. They relate the curvature of spacetime at every point to the distribution of mass and energy at that point. Solve the equations and you get a description of how spacetime is shaped. Once you know the shape, you can predict how objects will move. The equations are nonlinear, meaning they are hard to solve, and exact solutions are rare. Most problems in general relativity require approximations or numerical simulations, but for certain idealized cases, exact solutions exist. One of the first things Einstein did after finalizing the theory was calculate Mercury's orbit. He plugged the mass of the Sun into his equations and worked out how space-time curves in the Sun's vicinity. Then he calculated how Mercury moves through that curved space-time. The result was an orbit that precesses, not because of another planet, not because the Sun is oblate, just because space-time near the Sun is curved, and that curvature affects the motion in a way Newton's equations do not capture. The amount of precession Einstein's theory predicted was 43 arcseconds per century, exactly the discrepancy that had been puzzling astronomers for decades. No adjustable parameters, no fudge factors, just the equations predicting the observation with perfect accuracy. When Einstein saw that his theory explained Mercury's orbit, he later said he felt something snap inside his chest. He knew the theory was correct, not just approximately correct, fundamentally correct, a description of reality that went deeper than Newton ever could, and the implications extended far beyond Mercury. One of the most striking predictions of general relativity is that light bends in a gravitational field. In Newton's theory, light travels in straight lines. Gravity acts on objects with mass, and photons have no mass, so light is unaffected. In general relativity, light follows geodesics, the same as everything else, and geodesics in curved spacetime are not straight. If spacetime is curved by a massive object, light passing near that object will follow the curve. Its path will bend. Einstein calculated how much light from a distant star should bend if it passed close to the Sun. The prediction was about 1.75 arcseconds of deflection for light grazing the Sun's surface. That is a tiny angle, but measurable. The problem was that you cannot see stars near the Sun under normal conditions. The Sun is too bright. It drowns out the starlight. The only time you can see stars near the Sun is during a total solar eclipse, when the Moon blocks the Sun's light and the sky goes dark enough that stars become visible. In 1919, just a few years after Einstein published General Relativity, a total solar eclipse occurred. 2 expeditions were organized to observe it, one led by Arthur Eddington, traveling to the island of Príncipe off the coast of West Africa, the other to Sobral in Brazil. Both teams photographed stars near the Sun during the eclipse and measured their positions. Then they compared those positions to photographs taken of the same stars months earlier when the Sun was nowhere near them. If general relativity was correct, the stars photographed during the eclipse should appear shifted slightly outward, away from the Sun, because the Sun's gravity bent the light on its way to the camera. The results were announced in November 1919 at a joint meeting of the Royal Society and the Royal Astronomical Society in London. Eddington reported that the measured deflection was consistent with Einstein's prediction and inconsistent with the Newtonian value, which was half as large. The announcement made headlines. The New York Times ran the story under the headline, "Lights All Askew in the Heavens, Men of Science More or Less Agog Over Results of Eclipse Observations." Einstein became an international celebrity overnight. His theory had predicted something bizarre, light bending around the Sun, and observation confirmed it. General relativity was not just a better version of Newton, it was a different framework. And one of its most unsettling predictions was that under certain conditions, space-time could curve so severely that a boundary would form, a region from which nothing, not even light, could escape. Einstein himself did not believe this prediction was physical. He thought it was a mathematical artifact, something that popped out of the equations but did not correspond to anything real. He was wrong. Black holes are real, and they are the most extreme manifestation of what general relativity allows. The first exact solution to Einstein's field equations was found by Carl Schwarzschild in 1915, just months after the theory was published. Schwarzschild was serving in the German army on the Russian front during World War I. He contracted a painful autoimmune disease while in the trenches and continued working on the equations even as his health deteriorated. He sent his solution to Einstein by mail. Einstein presented it to the Prussian Academy of Sciences in January 1916. Schwarzschild died a few months later at the age of 42. Schwarzschild's solution describes the space-time geometry around a spherical, non-rotating mass. It is exact, meaning no approximations were made. And it contains something strange. At a specific radius, the equations behave oddly. That radius is now called the Schwarzschild radius, and it is given by a simple formula: 2 times the gravitational constant times the mass, divided by the speed of light squared. For an object with the mass of the Sun, the Schwarzschild radius works out to about 3 kilometers. For Earth, it is about 9 millimeters. The Schwarzschild radius marks the size of the event horizon for a black hole of a given mass. If you could compress the Sun down to a sphere 6 kilometers across, the entire mass packed into a region smaller than a city, the escape velocity at that surface would equal the speed of light. Compress it further, and the escape velocity exceeds the speed of light. At that point, nothing can escape, not matter, not radiation, not information. You have created a black hole. For decades, physicists argued about whether the Schwarzschild radius was a real physical boundary or just a mathematical quirk of the coordinate system used to describe the spacetime. It turns out the singularity at the Schwarzschild radius, the place where some of the equations blow up, is a coordinate singularity, not a physical one. You can choose different coordinates and the singularity disappears. The event horizon is a real boundary, but it is not a place where anything dramatic happens locally. An observer falling through the event horizon of a large black hole would not feel anything unusual. Space-time is smooth there. The geometry is curved, but not infinitely so. The real problem lies deeper, at the center. At the very center of a black hole, at what is called the singularity, the equations of general relativity predict that space-time curvature becomes infinite. Density becomes infinite, volume goes to zero. All the mass of the black hole is compressed into a single point with no size. This is not a place where the math gets messy. This is a place where the math stops working entirely. Infinite curvature means the equations are telling you they no longer apply. The theory has reached its limit. Most physicists do not believe the singularity is real in the way the equations describe it. Infinities in physics are almost always a sign that something is missing. General relativity is a classical theory. It does not account for quantum mechanics. At the scales where singularities would exist, quantum effects should dominate. The wavelengths of particles would be comparable to the size of the region itself. Quantum uncertainty would prevent anything from being localized to a point of zero size. Gravity itself should be quantized, meaning there should be a quantum theory of gravity that replaces general relativity in extreme regimes. We do not have that theory yet. Efforts to build one have been ongoing for decades. String theory, loop quantum gravity, and other frameworks attempt to unify general relativity with quantum mechanics, but none have been experimentally confirmed. The singularity at the center of a black hole is one of the places where a quantum theory of gravity would be needed to describe what actually happens. Until we have that theory, the singularity remains a question mark, a boundary where known physics breaks down and we are forced to admit ignorance. The singularity problem is not unique to black holes. The Big Bang, the moment the universe began, is also described by general relativity as a singularity, a point of infinite density and temperature where space-time itself came into existence. Most cosmologists believe the true beginning of the universe involved quantum gravitational effects that smoothed out the singularity. But again, we do not have the tools to calculate what those effects were. Singularities are reminders that our current theories, as successful as they are incomplete. In 1965, Roger Penrose proved a theorem that made the singularity problem unavoidable. Penrose showed that once a certain amount of mass collapses past a certain point, a singularity must form. Not might form, must form. This was not an argument based on symmetry or idealized conditions. It was a general result. The formation of singularities is generic in general relativity. You cannot avoid them by arranging the collapse carefully or adding rotation or doing anything clever. If enough mass is compressed into a small enough region, a singularity will appear. Penrose won the Nobel Prize in 2020 in part for this work. The theorem does not tell you what happens at the singularity. It just tells you that the equations predict one will form, and that within a finite amount of proper time, anything falling into a black hole will reach it. The singularity is not a place far in the future. It is not something you can avoid by slowing down or changing direction. Once you cross the event horizon, the singularity is in your future the way tomorrow is in your future. You will reach it, and when you do, the equations say the tidal forces become infinite. You are crushed to zero volume. That is what the math says. Whether nature actually does this is unknown. One of the strangest consequences of general relativity inside a black hole is that space and time swap roles. Outside the event horizon, time is what you move forward through. You can move backward and forward in space, but you are always moving forward in time. Inside the event horizon, this changes. The direction that used to be time becomes space. The direction that used to be toward the singularity becomes the future. You can no more avoid moving toward the singularity than you can avoid moving into the next second outside a black hole. It is not a place, it is a moment, and every possible future you could have leads to that moment. This is hard to visualize because it is not something we experience. We are built to navigate a universe where space is space and time is time. Inside a black hole, the geometry is so warped that those labels lose their normal meaning. The singularity is less like a location at the center and more like an event that will happen to you. You cannot steer away from it any more than you can steer away from next Tuesday. General relativity also predicts that time runs at different rates depending on where you are in a gravitational field. Clocks closer to a massive object tick slower than clocks farther away. This is called gravitational time dilation, and it is not a small effect near a black hole. A clock sitting just outside the event horizon of a stellar mass black hole, as measured by a distant observer, would appear to tick so slowly that it would take an infinite amount of time to reach the horizon. An object falling toward a black hole would appear to slow down, redden, and fade as it approached the horizon, asymptotically freezing at the edge. But from the perspective of the falling object, time passes normally. The clock on your wrist keeps ticking at its usual rate. You cross the event horizon in finite time. There is no moment where you freeze, no moment where time stops. You just keep falling, and from your perspective, everything is smooth until the tidal forces become strong enough to tear you apart. This difference in perspective is one of the deepest features of general relativity. Space-time is not absolute. Measurements of time and distance depend on your motion and your position in the gravitational field. What looks like an infinite amount of time to one observer is a few seconds to another. Both perspectives are valid. Both are describing the same event, but the descriptions are radically different. Black holes are the ultimate test of general relativity because they push the theory into regimes where gravity is as strong as it can possibly be without requiring a quantum description. Near the event horizon, space-time is curved sharply, but not infinitely. The theory makes definite predictions. The size of the event horizon, the bending of light, the precession of orbits, the gravitational redshift of signals, all of these can be measured, and so far, every measurement agrees with the predictions. The images from the Event Horizon Telescope showed shadows with sizes matching the theory to within a few percent. The orbits of stars around Sagittarius A star show precession and time dilation consistent with general relativity. The gravitational waves detected by LIGO, emitted by merging black holes, match the waveforms predicted by simulating Einstein's equations on supercomputers. There is no evidence yet that general relativity fails near black holes. It might fail inside the event horizon, where quantum effects should matter. It might fail at the singularity, where the equations themselves break down. But at the horizon and in the region just outside, the theory works perfectly. This is both reassuring and unsettling. Reassuring because it means we understand black holes better than we have any right to. A theory developed more than a century ago, based on thought experiments about elevators and trains, correctly predicts the behavior of the most extreme objects in the universe. Unsettling because it means we are still operating within a framework that we know is incomplete. General relativity does not include quantum mechanics. Quantum mechanics does not include gravity. Somewhere, at some scale, the two theories must merge. Black holes are where that merger is most urgently needed. The singularity is the smoking gun. It is the place where general relativity admits it cannot continue. The equations produce infinities, and infinities are physics giving up. They are not predictions, they are warnings. Warnings that say you need a better theory. Until we have that theory, the singularity will remain a mystery. A point on the map, marked here, be dragons. A region we can point to, describe mathematically, but not truly understand. And yet black holes exist. We have imaged their event horizons. We have measured their masses. We have detected the gravitational waves they emit when they collide. They are not speculation, they are objects, sitting out there in the universe, real and measurable. General relativity predicted them, and observation confirmed them. The theory works. Even in places where it should not, even in places where we expect it to break down eventually. That is the legacy of Einstein's equations. They describe a universe stranger than anything Newton imagined. A universe where space and time are flexible, where mass bends geometry, where gravity is not a force, but a curvature, where objects as massive as millions of suns can be compressed into regions smaller than the solar system, warping space-time so severely that they trap light itself. Black holes are not anomalies, they are natural consequences of the equations, features of the geometry that must exist if the theory is true, and they are also laboratories, places where space-time is stretched to its limits, where we can test whether general relativity still holds or whether cracks begin to show. Every observation of a black hole, every measurement of an orbit or a shadow or a gravitational wave is another data point, another test, another chance to see if the theory that has guided us for more than 100 years continues to work, or whether something new is waiting to be discovered. So far, the theory holds. The universe continues to behave the way Einstein said it would. Space-time curves, light bends, time dilates, black holes exist, and at their centers, hidden behind event horizons that nothing can cross outward, there may be singularities where the equations fail and reality becomes something we do not yet have the language to describe. Or there may be something else, something quantum, something smooth, something that prevents the infinity and replaces it with structure we cannot yet see. We do not know. But we know where to look. At the centers of galaxies, at the endpoints of stellar collapse, at the boundaries where light stops escaping and space-time folds in on itself. Black holes are not just objects, they are questions. Questions about the nature of space, time, gravity, and the limits of what we can know. And every answer we find leads to another question deeper still, which is exactly where we are heading next. Because black holes do not just warp space, they warp time. And that warping turns them into something unexpected: archives, records, cosmic time capsules that may hold information about the universe's entire history, written into the geometry of space-time itself. We left off at the boundary where known physics breaks down, singularities, infinities in the equations, regions where general relativity admits it cannot continue. Black holes as questions, not just objects. Questions about space and time and the limits of what we can know. And at those limits, something strange happens. Black holes, the ultimate destroyers, the cosmic shredders that tear apart everything they touch, might also be the universe's most faithful archivists, keepers of information, records written in the geometry of space-time itself. That idea sounds absurd. How can an object defined by what it hides, by what it traps behind an event horizon no signal can cross, be a keeper of anything? If information falls into a black hole, it is gone, lost, sealed behind a boundary that nothing escapes. That is what we have been saying for 6 chapters. That is what the event horizon means: one-way door, point of no return. Except in 1974, Stephen Hawking realized something that no one had expected. Black holes are not entirely black. Hawking was working on the problem of how quantum mechanics behaves near an event horizon. Quantum mechanics, the theory that describes the behavior of particles at the smallest scales, has a strange feature. Empty space is not actually empty. It seethes with activity. Pairs of particles and antiparticles pop into existence constantly, borrowing energy from the vacuum, existing for a tiny fraction of a second, then annihilating each other and paying the energy back. This happens everywhere, all the time. It is called quantum fluctuation, and it is a consequence of the uncertainty principle. You cannot have a region of space where the energy is exactly zero for any extended period. The vacuum fluctuates. Normally, these fluctuations are invisible. The particle pairs appear and disappear so quickly that they have no measurable effect on anything. But near an event horizon, the situation changes. If a particle-antiparticle pair pops into existence right at the edge of the horizon, one of the particles might fall into the black hole while the other escapes. The escaping particle is real. It carries energy away from the black hole. The infalling particle, in a sense, carries negative energy inward, reducing the black hole's total mass. The net result is that the black hole loses energy. It radiates, not because anything is coming out from inside the horizon, but because the quantum vacuum near the horizon is producing particles, and the geometry is such that some of those particles escape. Hawking calculated the spectrum of this radiation. It turns out that a black hole radiates as if it were a hot object, a black body, with a temperature determined by its mass. The smaller the black hole, the hotter it is. The formula is simple. The temperature is inversely proportional to the mass. Double the mass, and the temperature drops by half. Halve the mass, and the temperature doubles. For a black hole with the mass of the Sun, the Hawking temperature works out to about 1/10,000,000th of a degree above absolute zero. That is cold, far colder than the cosmic microwave background, the faint afterglow of the Big Bang, which sits at about 3 degrees above absolute zero. A solar mass black hole is not radiating faster than it is absorbing radiation from the surrounding universe. It is not losing mass, it is gaining mass. For a 3 solar mass black hole, the kind formed from a collapsing star, the temperature drops even further. Estimates put it at around 1/10,000,000th of a degree. At that temperature, the power output is absurdly small. The black hole is radiating, yes, but so faintly that detecting it would be impossible. The radiation is drowned out by every other source of heat in the universe. The cosmic microwave background alone is millions of times brighter. Hawking radiation from stellar mass black holes is, for all practical purposes, undetectable. But the radiation is there, and it has consequences. Because the black hole is losing energy, it is losing mass, slowly, incredibly slowly, but steadily. Over time, the black hole shrinks, and as it shrinks, its temperature rises, the process accelerates. A black hole that starts at 1 solar mass will take about 10 to the 64th power years to evaporate completely. That is a 1 followed by 64 zeros. For context, the current age of the universe is about 10 to the 10th power years, a 1 followed by 10 zeros. The evaporation time for a solar mass black hole is 10 to the 54th power times longer than the universe has existed so far. It is not a timescale that matters to anything happening now. Scale up to a 30 solar mass black hole, more typical of what you get from a collapsing star, and the evaporation time stretches to about 10 to the 61st power times the current age of the universe. These numbers are so large they stop meaning anything. You cannot visualize them, you cannot relate them to human experience. They are cosmological timescales, deep time, the kind of time that makes the age of stars look like an eye blink. But eventually, if the universe lasts long enough, black holes evaporate. The process is slow at first, almost imperceptible. The black hole loses mass, 1 Hawking particle at a time. As the mass decreases, the temperature rises, the rate of evaporation increases. In the final moments, when the black hole has shrunk down to a tiny mass, maybe a few thousand kilograms, the temperature spikes. The radiation output becomes enormous. The black hole evaporates in a final burst of energy, a flash of gamma rays, and then it is gone, no remnant. No leftover structure, just radiation scattering into space. The black hole has disappeared. This is not something we will ever observe. The smallest black holes expected to exist naturally weigh at least 2.5 to 3 solar masses. Those will take unimaginable spans of time to evaporate. By the time a stellar mass black hole begins to evaporate noticeably, every star in the universe will have burned out. Galaxies will have dissolved. The cosmic microwave background will have cooled to effectively zero. The universe will have entered what cosmologists call the dark era, a phase where no new stars form, no light is generated, and the only activity comes from the slow decay of matter and the evaporation of black holes. Even in the dark era, black holes will dominate. They will be the last massive structures left, and they will persist for timescales that make the current age of the universe look like the first second after the Big Bang. Supermassive black holes, the kind sitting at the centers of galaxies, will take even longer. A black hole weighing 1 billion solar masses will take roughly 10 to the 100th power years to evaporate. That is a Google years, a 1 followed by 100 zeros. Time on that scale is beyond comprehension. It is longer than any process we have ever observed or measured. It is longer than the predicted lifetime of protons, assuming protons decay at all. It is so long that by the time a supermassive black hole evaporates, the universe itself may have changed in ways we cannot predict. New physics may have emerged. The laws governing matter and energy may have shifted. We do not know. What we do know is that if Hawking is correct, black holes are not eternal. They are temporary. Extremely long-lived, yes, but not permanent. Given enough time, they all evaporate, and that raises a problem. A deep, unsettling problem that physicists have been arguing about for nearly 50 years, the information paradox. Information, in the physics sense, is not just data. It is the complete quantum state of a system. Every particle, every field, every property that defines what something is. Quantum mechanics says information is conserved. It cannot be created or destroyed. It can be scrambled. It can be spread out. It can be encoded in ways that make it impossible to read in practice. But the total information content of a closed system never changes. This is a foundational principle. Burn a book, and the information in that book is not destroyed. It is converted into the quantum states of the smoke particles, the ash, the photons emitted during combustion. If you could measure the exact quantum state of every particle produced by the fire, you could, in principle, reconstruct what the book said. You never will. The information is too scrambled, but it is not gone. Black holes seem to violate this rule. When something falls past the event horizon, its information disappears from the observable universe. You cannot retrieve it. You cannot measure it. You cannot reconstruct it. The black hole itself retains only 3 pieces of information: its mass, its electric charge, and its angular momentum. Everything else is erased. The object that fell in could have been a grand piano, or a cloud of hydrogen atoms, or a spacecraft full of encyclopedias. The black hole does not care. As long as the mass, charge, and spin are the same, the resulting black hole is identical. John Wheeler called this the no-hair theorem. Black holes have no hair, no distinguishing features, no memory of what fell in. That is a problem because quantum mechanics says the information should still exist. It should be encoded somewhere. If the information is truly destroyed, quantum mechanics is wrong. If quantum mechanics is right, the information must be preserved somehow. But where? Inside the event horizon, sealed off forever? Encoded on the surface of the horizon in some way we do not understand? Leaking out slowly in the Hawking radiation? The third option is the most interesting. Hawking originally calculated that the radiation emitted by a black hole is purely thermal. It has no structure, no information content. It is just random heat. If that is true, and if the black hole eventually evaporates completely, then the information that fell in is gone, destroyed, lost when the black hole disappeared. That would mean quantum mechanics is wrong at a fundamental level, or at least incomplete. It would mean there are situations where information is not conserved. Most physicists find that conclusion unacceptable. The conservation of information is too deeply embedded in quantum theory to discard easily. So for decades, researchers have been trying to figure out how the information might be preserved. One possibility is that the Hawking radiation is not actually random. Maybe it contains subtle correlations, patterns too faint to detect with current tools, that encode the information of everything that fell in. The encoding would have to be incredibly dense. Every bit of information from every object that ever crossed the horizon, all of it somehow imprinted into the outgoing radiation. The mechanism for how that could work is unclear, but if it does, then black holes do not destroy information. They transform it, scramble it beyond recognition, but preserve it. Another possibility is that the information is stored on the event horizon itself. This idea comes from the holographic principle, a concept that emerged from string theory and black hole thermodynamics. The principle says that all the information contained in a volume of space can be encoded on the boundary of that volume. For a black hole, the boundary is the event horizon. Everything that falls in might leave an imprint on the horizon, a kind of two-dimensional hologram that contains the full three-dimensional information. The horizon becomes a surface covered in encoded data, a record of everything the black hole has ever consumed. When the black hole evaporates, the information encoded on the horizon is released into the Hawking radiation, slowly over immense timescales, but released. The idea is strange. It suggests that the three-dimensional space we experience is in some sense a projection from information stored on a two-dimensional surface. It implies that the universe itself might be a hologram, that the volume of space we live in is less fundamental than the boundaries enclosing it. These are not idle speculations. They are serious proposals coming out of attempts to unify quantum mechanics and general relativity, and they have implications far beyond black holes. A third possibility is that information is not lost because black holes do not fully evaporate. Maybe the evaporation process stops before the black hole disappears completely. Maybe it leaves behind a remnant, a tiny stable object that contains all the information. The problem with this idea is that the remnant would have to be incredibly small, much smaller than an atomic nucleus, and yet contain an arbitrarily large amount of information. That sounds impossible. It would violate bounds on how much information can be stored in a given volume. But some researchers think it is worth considering because the alternative, information destruction, is even more problematic. Or maybe the paradox points to something deeper. Maybe the very idea of information falling into a black hole and being lost is based on a flawed understanding of what happens at the horizon. Maybe there is no sharp boundary. Maybe quantum effects smooth out the horizon in a way that prevents information from ever truly crossing. Maybe what looks like an event horizon from far away is, up close, something more complicated. A firewall, a fuzzy membrane, a region where space-time itself breaks down into something we do not have the language to describe. These are speculative ideas, attempts to resolve the paradox by rethinking what a black hole is at the quantum level. None of them have been confirmed. None of them have made predictions that we can test with current technology. What we are left with is a question. Does the information that falls into a black hole survive, or is it destroyed? Both answers have consequences that challenge fundamental physics. If it survives, we need a mechanism to explain how it gets out. If it is destroyed, we need to revise quantum mechanics to allow for information loss under certain conditions. Neither option is comfortable, and after nearly 50 years of work, the paradox remains unresolved. But there is another way to think about black holes and information, not as destroyers or cryptic encoders, but as archives, keepers. Black holes accumulate everything that falls into them. They do not digest it or break it down chemically. They just add it to the total mass. Every star that gets torn apart, every gas cloud that spirals inward, every stray photon that crosses the horizon, all of it contributes. The black hole grows, and in growing, it records, not in a way we can read, not in a way that stores the information accessibly, but in the sense that its total mass, Its total energy reflects everything it has consumed. In the far future, in the dark era, when stars are gone and galaxies have dispersed and the universe is cold and empty, black holes will be the dominant structures. They will sit in the voids, slowly radiating, slowly shrinking, carrying within them or on them or encoded in their radiation the accumulated history of everything that fell in over billions or trillions or quadrillions of years. They will be time capsules, not intentional ones, not designed to preserve information, but capsules nonetheless, holding within their event horizons the imprint of stars and planets and perhaps civilizations, all compressed into the geometry of space-time. If information is truly encoded in Hawking radiation, then the radiation itself becomes the message. A stream of particles carrying the quantum history of the black hole's entire existence, emitted over timescales so long that no one will be around to receive it. The universe will have moved on. Entropy will have won. The black hole will evaporate into a cold, dark, expanding void, and the information it carried will scatter into radiation that no detector will ever measure. That is the fate of black holes. Not dramatic, not sudden, just a slow fading over timescales that make eternity look brief. And in that fading, they will release everything they ever captured. If the information is preserved, if the paradox resolves in favor of conservation, if Hawking radiation really does carry the encoded quantum states of every particle that ever crossed the horizon, we do not know yet. The paradox remains open. But the implications are vast, because if black holes preserve information even in scrambled form, then they are not just endpoints, they are not just graves where matter goes to die. They are also libraries, archives, records of cosmic history written in a language we are only beginning to learn to read, the language of quantum gravity, the language of space-time geometry, the language that describes what happens when matter and energy are compressed so tightly that the universe itself warps around them. Stephen Hawking changed his mind about the information paradox late in his life. In 2004, he conceded that information is probably not destroyed. He proposed that the information does escape, encoded in subtle correlations in the Hawking radiation. He admitted he had been wrong in his earlier stance, though the mechanism he proposed was not universally accepted. Other physicists continue to debate. Some think the information is lost, some think it is preserved. Some think the question itself is malformed, that we are asking the wrong thing because we do not yet understand what information means in the context of quantum gravity. What is clear is that black holes are not simple. They were never simple. They looked simple. Spheres of nothing, regions where light cannot escape. But the deeper we look, the more layers we find. Event horizons that are also holographic surfaces. Singularities that might not be singular, radiation that carries heat and possibly information, objects that connect thermodynamics, quantum mechanics, and general relativity in ways that challenge our understanding of all three. And they last, they persist, they are patient. In a universe where stars burn out and galaxies fade and protons might eventually decay, black holes remain. They are the longest-lived structures the universe knows how to build. They will outlast everything else. They will sit in the dark, alone, radiating faintly, shrinking by infinitesimal amounts, holding within or upon them the history of the universe they inherited. If we could somehow read that history, decode the information locked in their geometry or their radiation, we would have access to a record unlike anything else, a record spanning billions of years, a record that includes not just what fell in recently, but everything that fell in across the black hole's entire existence. Stars from the early universe, gas clouds enriched with the first heavy elements, planets, perhaps life, all of it compressed, scrambled, encoded, waiting, not for us. We will be gone long before black holes finish evaporating, but waiting nonetheless. Recorded in the structure of space-time itself, that is the paradox. Black holes are destroyers and archivists. They erase structure and possibly preserve information. They are the ultimate endpoints and possibly the ultimate keepers. They hide everything behind an event horizon and possibly encode everything on that horizon's surface. They are questions that force us to confront the limits of what we know and the gaps in our theories, and they are also beacons, markers of where new physics must lie, where general relativity and quantum mechanics finally collide and something new emerges. We do not have that new physics yet. We do not have a theory of quantum gravity that resolves the information paradox cleanly. We do not have a complete description of what happens at a black hole's center or on its horizon, but we know where to look. We know black holes are the key, and we know that understanding them fully will require rethinking everything we think we know about information, entropy, space, and time. That is where the field is heading. Not just observing black holes from a distance, not just measuring their masses and spins and shadows, but probing the quantum mechanics of their horizons, testing whether information escapes, searching for deviations from general relativity that might point the way toward a deeper theory. And as technology improves, as telescopes get sharper and detectors get more sensitive, we move closer to answering the question that has haunted physics since 1974. When something falls into a black hole, is it gone forever, or does the universe keep a copy? We left off at the edge of knowledge, information paradoxes, singularities hidden behind event horizons, black holes as possible archivists, keepers of cosmic history, encoded in geometry or radiation or some mechanism we do not yet understand. Questions that have haunted physics for 50 years. Questions that remain open because the tools we need to answer them are still being built, but they are being built right now. And in the next few decades, those tools are going to transform what we know about black holes from a catalogue of observations into something deeper, a map of how these objects connect to the rest of physics, how they form, how they grow, how they merge, how they die, and what they can tell us about the universe itself. The next era of black hole research will not look like the last one. For most of the 20th century, black holes were studied one at a time. Find a candidate, measure its mass, watch stars orbit it, or track X-rays from its accretion disk. Build a case, publish a paper, move on to the next one. It was careful work, precise work, but it was also slow. Each black hole was a separate investigation, a separate puzzle. The field accumulated knowledge, the way geology accumulated rock samples, one specimen at a time. That is changing. The future of black hole research is not about finding individual objects. It is about finding populations, catalogues. Hundreds or thousands of black holes detected simultaneously, their properties measured in bulk, their distributions mapped across cosmic time. And the key to unlocking that future is a technique that did not exist as a practical tool until less than a decade ago: multi-messenger astronomy. The term sounds technical. It is not. Multi-messenger astronomy just means observing the same event using more than one kind of signal. Light is one messenger. We have been using it for centuries. Telescopes collect photons, and from those photons we build images, spectra, measurements of brightness and color and motion. Light is versatile. It carries information across vast distances, but it is not the only messenger the universe sends. There are also neutrinos, nearly massless particles that pass through matter almost without interacting. There are cosmic rays, high-energy particles accelerated to extreme velocities by violent processes. And there are gravitational waves, ripples in space-time itself, emitted by accelerating masses traveling at the speed of light, carrying information about the motion and structure of the objects that produced them. Each messenger tells a different part of the story. Light shows you what is hot, what is radiating, what is being illuminated by surrounding material. Neutrinos show you what is happening deep inside dense regions where light cannot escape. Cosmic rays show you where particles are being accelerated to extreme energies. Gravitational waves show you the motion of massive objects, the dynamics of space-time itself, events that might produce no light at all. Observe an event with multiple messengers and you get a complete picture, a three-dimensional view of what is happening, context that no single messenger can provide. For black holes, multi-messenger astronomy became practical on September 14, 2015. That was the day LIGO, the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the first time. The signal came from two black holes colliding about 1.3 billion light-years away. One black hole weighed 36 solar masses, the other weighed 29. They had been orbiting each other for millions or billions of years, spiraling closer as they radiated gravitational waves, losing energy, tightening the orbit. In the final moments, they were orbiting each other hundreds of times per second, moving at a significant fraction of the speed of light, warping space-time so violently that the ripples were detectable across more than 1 billion light-years of space. The merger took a fraction of a second. The two black holes collided, their event horizons touched, and they became one. The resulting black hole weighed 62 solar masses. That is 3 solar masses less than the sum of the original two. The missing mass, about 3 times the mass of the Sun, was converted directly into gravitational wave energy. 3 suns worth of mass turned into ripples in space-time, radiated outward in all directions at the speed of light. The amount of power emitted during the peak of the merger, for that brief fraction of a second, exceeded the combined light output of every star in the observable universe. Not by a little, by a factor of 50. The merger was the brightest event in the universe at that moment. And it produced no light, no photons, no electromagnetic signal of any kind, just gravitational waves. LIGO detected those waves as a chirp, a rising tone lasting about 1/10 of a second. The frequency started low, around 35 Hz, and climbed to about 250 Hz before cutting off. The sound, when played through speakers, sounds almost musical, a rising pitch, a brief peak, then silence. That chirp encoded the entire history of the merger, the masses of the two black holes, their spins, the distance to the event, the orientation of their orbit relative to Earth. All of it could be extracted from the waveform by comparing the signal to simulations run on supercomputers. The agreement was nearly perfect. The detected signal matched the predictions of general relativity for a black hole merger with those specific parameters. The detection was announced in February 2016, 5 months after the event, and it changed the field overnight. Gravitational wave astronomy, which had been theoretical for a century, was suddenly real, practical. And black holes, which had been invisible except for the light of material falling into them, were now detectable directly through the space-time distortions they create when they merge. LIGO had opened a new window on the universe, a window that sees things no telescope ever could. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of black hole mergers. Some involve black holes much larger than the first pair. Some involve black holes spinning at different rates. Some involve unequal mass ratios, where one black hole is significantly heavier than the other. Each detection adds to the catalogue. Each waveform provides data, and patterns are starting to emerge. The mass distribution of black holes, the rate at which they merge, the environments where mergers are most common. Questions that could only be guessed at before are now being answered with data. One of the most surprising findings is that black hole mergers are relatively common. LIGO and Virgo estimate that within a sphere 1 gigaparsec across, about 3 billion light-years in diameter, a black hole merger occurs roughly once every 10 minutes. That is just the mergers detectable by current instruments. Smaller mergers, or mergers at greater distances, go undetected. The true rate is likely higher. The universe is full of black holes colliding, merging, radiating gravitational waves that no one hears because the signal is too faint or the detectors are not sensitive enough. But with each improvement in detector sensitivity, the range increases, the volume of space monitored grows, and the number of detections climbs. Gravitational waves are also beginning to shed light on one of the biggest mysteries in black hole physics: intermediate mass black holes, the missing link. Stellar mass black holes, the kind formed from collapsing stars, weigh between about 5 and a few dozen solar masses. Supermassive black holes, the kind sitting at galaxy centers, weigh millions or billions of solar masses. But between those two ranges, between a few dozen and a few 100,000 solar masses, confirmed black holes are rare, almost non-existent. There are candidates, objects that might be intermediate mass black holes based on indirect observations, but no definitive detections. The gap is puzzling because intermediate mass black holes should exist. They are the natural stepping stones from stellar mass to supermassive. Without them, it is hard to explain how supermassive black holes grew so large, so quickly in the early universe. Gravitational wave detectors might be the tool that finds them. A merger between a stellar mass black hole and an intermediate mass black hole would produce a gravitational wave signal distinct from the mergers LIGO has been detecting. The waveform would be longer, the frequency would be lower, the signal would carry information about a mass range that optical and X-ray telescopes struggle to access. So far, no clear intermediate mass black hole mergers have been detected, but the possibility is there. Future detectors, more sensitive and tuned to lower frequencies, are expected to probe this gap systematically. If intermediate mass black holes exist in significant numbers, gravitational wave astronomy will find them. The next generation of gravitational wave detectors is already being planned. LIGO and Virgo are ground-based interferometers, sensitive to frequencies between about 10 Hz and a few thousand Hz. That range is ideal for detecting stellar mass black hole mergers, but it misses the lower frequencies where supermassive black hole mergers would be visible. For that, you need a detector in space, free from seismic noise, free from Earth's vibrations, capable of measuring much longer wavelengths. The planned detector is called LISA, the Laser Interferometer Space Antenna. It will consist of 3 spacecraft arranged in a triangle, separated by about 2.5 million kilometers, roughly 6 times the distance from Earth to the Moon. Lasers will link the spacecraft, measuring the distances between them with extraordinary precision. When a gravitational wave passes through, the distances change, the triangle distorts. The detectors measure that distortion and reconstruct the waveform. LISA will be sensitive to frequencies between about 1/10,000th of a Hertz and 1 Hertz, a range completely inaccessible to ground-based detectors. That range includes the gravitational waves produced by supermassive black hole mergers, by intermediate mass black hole mergers, and by other exotic sources like orbiting white dwarf binaries and extreme mass ratio inspirals, where a stellar mass object spirals into a supermassive black hole over the course of years. LISA is scheduled to launch sometime in the mid-2030s. When it comes online, it will see a different universe than LIGO sees. LIGO sees the endpoints of stellar evolution, black holes formed from collapsing stars, merging in the local universe. LISA will see the collisions of the giants, supermassive black holes at the centers of galaxies, merging when their host galaxies collide. Those mergers take millions of years to complete. The black holes orbit each other for eons, spiraling inward, radiating gravitational waves the entire time. LISA will detect the final stages, the last few years before the merger, and possibly the merger itself. The waveforms will encode the masses, the spins, the distances, and the properties of the spacetime around the black holes. General relativity will be tested in regimes where gravity is stronger than anywhere LIGO can probe. One of the predictions LISA might test is whether event horizons really exist. This sounds strange. We have imaged event horizons. We have photographed their shadows. But those images show the region just outside the horizon. They do not prove that the horizon itself is a true one-way boundary with nothing inside. Some alternative theories propose that black holes do not have event horizons at all, that they are exotic compact objects with surfaces that prevent total collapse. LISA, by detecting the late stages of supermassive black hole mergers, could distinguish between a true black hole merger and the merger of exotic objects without horizons. The waveforms would be different, subtly but measurably. If the detected signals match the predictions for horizon mergers, that is another confirmation of general relativity. If they do not, if there are deviations, it would be the first direct evidence that black holes are not quite what we think they are. Multi-messenger astronomy is not just gravitational waves. It also means coordinating observations across the electromagnetic spectrum. When LIGO detects a black hole merger, telescopes around the world and in space are alerted within seconds. They point at the region of sky where the signal came from, searching for light. Most black hole mergers produce no light. The black holes are isolated, surrounded by empty space, and the merger itself emits only gravitational waves. But some mergers might occur in dense environments, regions with gas or nearby stars. If gas is present, the merger could heat it, producing a burst of X-rays or gamma rays. If a star is close enough, the gravitational waves or the recoil of the newly merged black hole could disrupt it, triggering a tidal disruption event. Detecting light alongside gravitational waves would provide context. It would tell you where the merger happened, what the environment looked like, whether the black holes formed in isolation or as part of a binary system in a dense star cluster. One famous multi-messenger event involved not two black holes, but two neutron stars. On August 17, 2017, LIGO and Virgo detected gravitational waves from a neutron star merger about 130 million light-years away. Unlike black hole mergers, neutron star mergers produce light, a lot of light. The collision ejected material at high speed, and that material, rich in heavy elements, glowed as it expanded and cooled. Telescopes detected the flash across the spectrum, from gamma rays to radio waves. The event confirmed that neutron star mergers are the sites where heavy elements like gold and platinum are forged. It also provided a new way to measure the expansion rate of the universe, independent of other methods. The combined gravitational wave and electromagnetic observations yielded an estimate for the Hubble constant of about 70 kilometers per second per megaparsec, with uncertainties of +12, -8. That is right in the middle of the disputed range. Not precise enough to settle the Hubble tension, but a proof of concept, a demonstration that multi-messenger observations can constrain cosmology. Black hole mergers with light are rarer, but they are expected. Some theoretical models predict that black holes in active galactic nuclei, the bright cores of galaxies where supermassive black holes are feeding, might merge while embedded in the accretion disk. The merger would disturb the disk, creating shocks, heating the gas, producing a flare visible across millions of light years. Detecting such an event would be a major discovery. It would tell us that some supermassive black holes grow not just by accreting gas, but by merging with other black holes. And it would provide direct evidence that mergers can happen in environments very different from the isolated vacuum where most LIGO detections occur. Another frontier is neutrinos. Neutrinos are produced in high-energy processes like the collapse of massive stars or the annihilation of matter near black holes. If a black hole is accreting material at a high rate, or if it is embedded in a dense environment where collisions and interactions are common, it might produce neutrinos. Detecting neutrinos from a black hole would open yet another messenger, another way to probe what is happening in regions too dense for light to escape. Neutrino telescopes like IceCube, buried deep in the Antarctic ice, are already searching for high-energy neutrinos from astrophysical sources. So far, they have detected neutrinos from distant galaxies, possibly from supermassive black holes in active galactic nuclei. But the signals are faint and the sources are not well localized. Future detectors, larger and more sensitive, will improve the chances of catching neutrinos from black hole-related events. The combination of gravitational waves, light, and neutrinos is what multi-messenger astronomy promises. Not one signal, not one perspective, a chorus. Multiple instruments, multiple wavelengths, multiple messengers, all pointed at the same event, all providing pieces of the puzzle. When it works, the result is transformative. The August 2017 neutron-star merger was a glimpse of what is coming, a single event observed by more than 70 telescopes and detectors worldwide. Gravitational waves detected by LIGO and Virgo, gamma rays detected by the Fermi satellite, optical light detected by dozens of ground-based telescopes, ultraviolet, infrared, and X-ray observations from space-based instruments, radio waves detected weeks later as the debris expanded. Every observation added information, every messenger contributed. The result was a complete picture of what happened, from the in-spiral to the collision, to the ejection of material, to the long-term aftermath. That is the future. Not isolated observations, coordinated campaigns, events dissected from every possible angle. The tools are improving. LIGO is undergoing upgrades that will increase its sensitivity by a factor of 2 or more. Virgo is being upgraded similarly. A third detector, Kagra in Japan, is coming online, adding another baseline to the network and improving the ability to localize sources. A fourth detector, LIGO India, is planned. More detectors mean better localization. Better localization means more telescopes can follow up quickly. More follow-up means more multi-messenger detections. The network is growing. The field is accelerating. And then there are the exotic ideas, the speculative possibilities that sit at the boundary between theory and fantasy. Micro-black holes, for example. These would be black holes much smaller than anything formed by stellar collapse. Black holes weighing kilograms or tons rather than solar masses. Theoretical physics allows them. Quantum gravity might produce them. Some models of the early universe predict that tiny fluctuations in density during the first fractions of a second after the Big Bang could have collapsed into primordial black holes of all sizes. Most would have evaporated by now, but some might still exist. Micro black holes are not astrophysical objects, they are quantum objects. If they exist, they would be governed by quantum mechanics as much as by general relativity. Stephen Hawking pointed out that small black holes evaporate faster than large ones. A micro black hole, weighing, say, 1 billion tons, would have a temperature of about 1 trillion degrees and a lifetime measured in seconds. It would radiate intensely, emitting particles and photons across the spectrum, until it evaporated completely in a final burst of energy. No such object has ever been detected. But if they exist, they might be detectable as brief flashes of gamma rays or cosmic rays appearing randomly across the sky, lasting milliseconds, then vanishing. Searches are ongoing. So far nothing, but the possibility remains. Another speculative idea is that black holes are portals, not in the science fiction sense of doorways to other dimensions, but in the sense that they might connect to other regions of spacetime. General relativity allows solutions where black holes are linked by structures called wormholes, tunnels through spacetime that connect distant regions. The catch is that these wormholes are unstable. They collapse almost as soon as they form, unless they are held open by exotic matter with negative energy density. No such matter is known to exist. The solutions are mathematically valid, but probably not physically real. Still, the possibility is intriguing. If wormholes exist, and if they are associated with black holes, then falling into a black hole might not end at a singularity. It might lead somewhere else. Another part of the universe. Another universe entirely. These are not ideas anyone takes seriously as descriptions of reality. They are thought experiments, explorations of what the equations allow. But they remind us that general relativity, even after more than a century, still contains surprises. The biggest question, the one driving most of the theoretical work, is how to unify general relativity with quantum mechanics. The two theories are incompatible at a fundamental level. General relativity describes gravity as smooth curvature of spacetime. Quantum mechanics describes everything else as discrete, quantized, probabilistic. General relativity is deterministic. Given the initial conditions, the equations tell you exactly what happens. Quantum mechanics is indeterminate. You can predict probabilities, but not specific outcomes. The two frameworks work beautifully in their own domains. General relativity explains planets, stars, galaxies, black holes, the expansion of the universe. Quantum mechanics explains atoms, molecules, chemistry, nuclear physics, particle interactions. But when you try to combine them, when you try to describe a system where both matter and gravity are important at quantum scales, the equations break down. Black holes are where the breakdown is most obvious. At the event horizon, general relativity works. Spacetime is curved, but the curvature is finite. Quantum effects are present but weak. You can ignore them and still get good predictions. But at the singularity, the curvature becomes infinite. The equations produce nonsense, infinities, divergences, predictions that do not make sense. Most physicists believe this is a sign that general relativity is not the final word. That at very small scales, or very high energies, or very strong curvatures, spacetime itself becomes something else, something quantum. Something we do not yet have a theory to describe. The search for a quantum theory of gravity has been ongoing for decades. String theory is one approach. It proposes that the fundamental objects in the universe are not particles, but tiny vibrating strings. Different vibrations correspond to different particles. One vibration is an electron, another is a photon. Another is a graviton, the hypothetical particle that mediates gravity. String theory naturally includes gravity. It unifies all forces into a single framework, but it requires extra dimensions, 10 or 11, instead of the 4 we experience. And it has not made any predictions that can be tested experimentally. It is mathematically rich, but empirically silent. Loop quantum gravity is another approach. It proposes that space-time itself is quantized, that at the smallest scales, space is not smooth but grainy, made up of discrete units. The geometry of space-time becomes a network of loops, a quantum foam. Loop quantum gravity predicts that singularities do not exist, that the infinite curvature at the center of a black hole is smoothed out by quantum effects. The collapse stops before reaching zero size. What replaces the singularity is unclear. Maybe a region of extremely high but finite curvature. Maybe a bounce, where the collapsing matter reaches a minimum size and then expands again, possibly into another universe. These are speculative ideas. Loop quantum gravity has not been developed far enough to make concrete predictions about black hole interiors. Other approaches exist: emergent gravity, causal set theory, asymptotic safety. Each proposes a different way to reconcile general relativity and quantum mechanics. None have succeeded completely. The problem is hard, perhaps the hardest problem in theoretical physics, and black holes sit at the center of it. Because black holes are the places where both theories must apply, where space-time is curved strongly enough that quantum effects cannot be ignored, where the singularity forces you to confront the limits of what general relativity can describe. The resolution, when it comes, will likely come from observations as much as from theory: multi-messenger astronomy, gravitational wave detections, measurements of black hole shadows with ever-increasing precision, tests of whether event horizons behave exactly as general relativity predicts, or whether there are deviations, hints of new physics. The next generation of detectors will probe closer to the horizon than ever before. LISA will measure supermassive black hole mergers with extraordinary precision. The Event Horizon Telescope is adding more sights, improving its resolution, aiming to image black holes in enough detail to see the photon ring structure, the multiple images of the accretion disk created by light orbiting the black hole multiple times. These observations will test general relativity in regimes it has never been tested before. And if the theory holds, that tells us something. If it breaks, if there are deviations, that tells us something else, something new, something that points toward whatever comes next. Black holes are not the end of the story. They are the beginning of the next chapter, a chapter we are only now starting to write. A chapter that will require new tools, new detectors, new ways of thinking about space and time. The universe has given us black holes as a gift. Not a comfortable gift, not an easy one, but a profound one. A set of objects so extreme, so unforgiving, that they force us to confront the limits of our understanding, to ask questions we do not yet know how to answer, to build instruments that did not exist a decade ago, to coordinate observations across the planet and across the electromagnetic spectrum, to listen to the universe not just with our eyes, but with our ears, through gravitational waves that carry the echoes of collisions billions of light years away. And the work continues. Right now, at this moment, detectors are running. LIGO is listening. Virgo is listening. Telescopes are scanning the sky. Computers are processing data. Researchers are building the next generation of instruments, planning the missions that will fly in the 2030s and 40s, writing the proposals that will shape the field for the next 50 years. Black holes were discovered on paper. They were confirmed by observation. They were imaged by a telescope the size of the Earth. And now they are being dissected, probed, tested, studied with a level of precision that would have seemed impossible just a generation ago. The future of black hole research is not about finding more black holes. It is about understanding the ones we have, about using them as laboratories, as tests, as keys to unlock the deeper structure of reality. Because black holes are not just objects in space. They are knots in space-time, places where the fabric of the universe is tied so tightly that it cannot untangle without help from a theory we do not yet have. And when we finally untie that knot, when we finally understand what happens at the singularity, what information means at the event horizon, how gravity and quantum mechanics merge, we will not just understand black holes, we will understand something deeper. Something about the universe itself, about how it works, what it is made of, what rules govern it at the most fundamental level. That is the promise. That is where the field is heading, into the unknown, into questions that have no answers yet, into observations that will take decades to complete, into theories that will require new mathematics, new physics, new ways of thinking. Black holes are the map. The observations are the journey, and the destination, when we finally reach it, will be an understanding of the universe that goes beyond anything we have now. Not just deeper, not just more precise, but fundamentally different. A view of reality that includes black holes not as anomalies or monsters or endpoints, but as natural, inevitable, essential features of a universe governed by laws we are only now beginning to grasp. That is the future. That is what the next generation of black hole research promises, and the work has already begun. We started with a heartbeat, a pulse buried in the seismic record of the planet, ticking away for 60 years with no explanation. We moved to galaxies that should not exist, sitting at the edge of the observable universe like facts that refuse to behave. We stood at the boundary where a supermassive black hole weighing millions of suns warps space-time so severely that light itself cannot climb back out. And we ended here, at the edge of knowledge, staring into questions that have no answers yet but demand to be asked anyway. Black holes are not just objects. They are not just cosmic curiosities sitting in distant galaxies, waiting to be catalogued and forgotten. They are the places where the universe shows its limits, where the equations that have guided us for more than a century start producing infinities and break down entirely, where space-time curves so sharply that the distinction between here and there, between now and then, stops making sense in the way we are used to. They are laboratories, tests, challenges written into the fabric of reality itself, daring us to figure out what happens when matter and energy are compressed past the point where anything we understand can continue. And the strangest part is that they are everywhere. 100 million of them scattered through the Milky Way alone, silent, invisible, patient, waiting not for us, but simply existing, following the rules, doing what collapsed stars do when there is nothing left to stop the collapse. The universe builds these things routinely, casually, as a natural consequence of how gravity works when you pack enough mass into a small enough space. We are the ones who find them strange. The universe does not care. It just keeps making them, one supernova at a time, adding to the collection, filling the galaxy with objects so extreme that studying them forces us to confront everything we do not yet know about space, time, information, and the boundaries of physics itself. That is the real power of black holes. Not that they destroy, not that they warp or trap or consume,